Are you speaking first?
I'll be speaking.
So this is your Zoom mic.
Yeah.
This is your in-room.
Okay. All right. In room, I probably won't need. I can project. Yeah. Yeah. All right. So do you want me to test this?
It's just,
Okay.
okay, cool.
Can you?
Oh,
Okay. Okay.
are we sharing the audio? Yes, she said she can hear it on Zoom.
Yeah. 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 Okay. All right.
Well, I guess you're good.
Okay. The camera set up over here. Good. So I can stand here.
Yep.
Perfect. Yeah.
Back there.
Yeah. They're controlling it back there. All right. Sounds good. Yeah.
And to turn this on and off, you just hold that down until the light.
All good. All right. Right, guys, let's get these proceedings underway. My name is Sanjeev Khudanpur. I'm a professor here in electrical engineering. I'm the director of the Center for Language and Speech Processing. And perhaps what's relevant to you today, along with my colleague, Dr. Livni Paula Garcia Pereira, and Ruth Scally, who's the Senior Administrative Coordinator. We are the organizers of this workshop. So you've all been corresponding with one of us over the last several months. So on behalf of the three of us, plus a few other people I'll introduce in a minute, let me welcome you all. So welcome to Baltimore, welcome to Johns Hopkins, welcome to the Frederick Jelinek Memorial Workshop on Speech and Language Processing. And within that, welcome to the NACL-sponsored summer school. So NACL is the North American chapter of the Association for Computational Linguistics. They're sponsoring the cost of having these 2-week tutorials. So welcome. First, let me do a quick show of hands. Most of you here are actually for the full 8 weeks of the workshop, but some of you are here just for the summer school. So all those who are here just for the summer school, raise your hands. 1, 2, 3, 4, 5, 6. Okay, so welcome. Enjoy your 2 weeks. Get as much of it out of it as you can. And later on, many of the talks and other things in the main workshop will be streamed live, so feel free to join them. And if you're in Baltimore, just come by to the talks if you like. There'll be plenary lectures, other things. So participate remotely as much as you feel like. And now, all those who are here for 8 weeks, raise your hands. Okay, is anybody not sure how long they're here? Okay, all right. So for you guys, this is just the beginning of the first 2 weeks. This is the beginning of the workshop. What we do is, the main workshop, as you all know, is focused on doing research in all aspects of speech and language technologies. And you've probably seen the workshop web pages, know the 4 teams and everything. These 2 weeks are meant to more like bring everybody up to speed, because different students come with different backgrounds. And we don't want you to full focus just on what your team leader tells you to do for the next 6 weeks. We want you to really understand what the other teams are doing, what the various issues in today's science and technology are. And so these 2 weeks are meant to be like a crash course to bring you all up to speed. If you tally up the hours of instruction that you get over here, it is about 1.5 semesters worth of a course. So you're going to get information like drinking from a fire hose, absorb as much as you can. We will record all the lectures. Unfortunately, we can't record the labs because those are hands-on activities, and they will be available afterwards. So if you want to refer back to these lectures, they'll be available to you afterwards. Make notes and keep in touch with the various instructors. Everybody who's teaching you over the next 2 weeks is an academic, including someone like people from Facebook and Meta who used to be academics, and they will all happily continue teaching you as if you need help after the 2-week tutorial. All right, so let's see, what all do I have? So I won't say a whole lot about the workshop itself. Maybe I'll give you a little bit of history. This is the 30th year in which we are having the workshop at Johns Hopkins. So you're actually coming here following a very long tradition. And it is the 29th workshop at Johns Hopkins because we had to skip 1 year due to COVID. But if you want to add it a different way, the workshop actually started at Rutgers University, and it was there for 2 years. So if you add that, there's the 31st workshop. The summer school bit is a little bit newer. And when I say a little bit newer, it means we started in 98. So it's only 26 years old. And the reason we started that is because the early editions of the workshop didn't have students. They only had senior researchers coming together. Once we started bringing in students, we realized that the students would sort of only know what they were doing and not know what the other teams are doing. So no, that's not fair. We should get everybody up to speed. So that's when this tradition started. And around 2000 something, NACL joined in and said, hey, this is a very good thing. We want to support this as a community activity. So NACL has been supporting us also for 20 some years. So that's the history. I won't say more. There's a whole lot more to tell you. Those of you here for 8 weeks, I'll give a longer introduction to the workshops on the first day. You'll hear more about that. So that's about the workshop. Any questions about the workshop history? Anything else? Okay, well, one small tidbit. We used to have it in continuously at Hopkins until 2014. And then starting 2014, I realized that I'm stuck here in Baltimore every summer, whereas other people come here to have fun. So I said, we'll go somewhere else instead. So starting 2014, we're doing 1 year away, 1 year here. We went to Prague, Seattle, Pittsburgh, Montreal, Le Mans in France. This year we're here. Next year we're going to go to Brno. So The workshop is now traveling. So hopefully some of you come back next year, it'll be another place. All right, that's pretty much all the history I want to tell you. Logistics. The reason I wanted to speak first before everybody else today is because I wanted to give you a little bit of information. So as you already know, if you want to be friendly, you can call her Paula. If you need something from her, call her Dr. Garcia. She and I are the main organizers of the workshop, but the real work is done by a lot of other people. So first and foremost, you've all met Ruth Scally. So Ruth, her office is 2 floors above in this building, and Ruth sort of knows all things administrative. And so any help of administrative organizational nature, please ask Ruth. Ruth actually retired 2 years ago, but we wouldn't let her go. So she continues to work with us just for the workshop, comes in a couple of days a week. And she's going to be helped by 2 student assistants. One of them, Julia, was already here. The other one, I think, starts on Thursday. So when Ruth is not here, one of the 2 student assistants will be here, and they all sit on the 2nd floor. So any administrative help, oh, I lost my J card, where is XYZ? They're the people to go to. Usually it's good to write them email, because that way, even if they're not at the desk at the moment, they can get back to you later. But if you are more the interactive type of person like I am, just go up to their desks. Next, you should get to know Dan Mead. Dan over here is our sysadmin. He will help you set up in the lab in the afternoon. If you notice on your schedule, there's a half-hour window where there is no lab starting yet, but Dan will be there, and all of you get there early. Kevin will only start the lab at 1:30, but you can get there a little early, make sure the internet works for you. Dan, have you set up a printer already? So there's a printer there if you need to print your boarding passes or whatever it is, you're scheduled to go to DC to have fun, make sure that works, and so on and so forth. Right? That's fine. So this is the stuff. Who am I forgetting? Dan, Ruth, Paula, am I forgetting anyone? No, staff-wise, I think we covered. Okay, all right. Next up, locations. So let me orient you. This is north, that's east, west, south. We are in Hackerman Hall, and Hackerman Hall is where CLSP, the Center for Language and Speech Processing, by the way, that's our logo, and the university doesn't like it because it doesn't have the university branded colors, which is a dull blue and something. But we made this logo almost exactly 40 years ago now. So we're going to stick with it. So that's CLSP. We are located in this building. Ruth's office is where the CLSP admin office is. Paula and I are on the 3rd floor directly above here. So that's where we are. Many of the CLSP faculty, except maybe for Anjali and Mark, they're all in this building. So this is the main center of CLSP, but not the center of the workshop. The workshop itself is in the building to our south, Malone Hall. And in the first 2 weeks, we'll just use one of the rooms in Malone Hall. It's a computer lab. And later on, we'll spill into 2 other rooms. So all the workshop activity happens over there. There are labs or tables, and then you'll work over there. Third thing, to our east is Barton Hall. Barton Hall, by the way, Malone Hall is also the home of the computer science department on the upper 3 floors. And that's where you'll be. Barton is the home of electrical engineering, electrical and computer engineering. And that's where we have a lounge. So there's a nice open space. There's a coffee maker, sofas. There's even a little projector if you want to share YouTube or TikToks with your friends. And that's where you can hang out. And all of you who are staying here long-term should have a J card. And maybe some of the short-term people do too. So you can use your J card to get into the lounge. If you have a J card, doesn't open the lounge door, who do you go to? Ruth. Yes, exactly. She'll program you in. Right? Okay, good. So that's Barton. So Hackerman, Barton, Malone, food. So when you take a break for lunch, or if you want to get a coffee, the nearest place other than our own coffee maker is Levering. Levering is to the northeast. So Levering has a cafeteria. It's a university cafeteria. Unfortunately, in summer, they're only open till about 2 or 3 in the afternoon. Above on the upper floor of Levering, there's a coffee place called the Daily Grind. They make pretty decent coffee last time I checked. And I'm a tea drinker. That's why I don't drink too much coffee. So that's the food place. But Levering can get boring. After all, it is a university cafeteria. So a better place to go if you want choices is further east. Go out of Barton, keep going, cross the huge construction site, which is going to be the new student center, and you'll come to Charles Street, cross that, come to St. Paul Street. And St. Paul is where there are lots of restaurants, cookies, pizza, subs, whatever you want, right? There's even a Chipotle. Apparently, it's popular among students. So all that is over there. And then if you're interested in something a little bit different, south of us is our house. It's about a 10-minute walk. Our house has a very nice food court, about 10, 12 different kinds of food. It is meant to be like, a slightly upscale food court. So they have really nice choices. There's a sushi place, there is an Egyptian street food place, there's bibimbap, all sorts of fun stuff. So our house, St. Paul Street, that's where you go. Our house has a bar, opens at about 10 in the morning. I know, but so you can go there and have food, right? So those are the places. There's another fun place, little known secret on campus. If you're willing to walk another 10, if you're willing to walk 10 hours northeast again, there's a building called the Mueller Building. It hosts something called the Space Telescope Science Institute, and they have a very nice cafeteria in there as well. There's one of the few little secrets of campus. People in Hopkins don't know about it, but if you've been in Hopkins long enough, you do. So those are your meal options. What else should I tell you about logistics? Meals, commute. Most of you have from out of town and we are hosting you. You're staying at Campion Tower, which is part of Loyola University. Campion Tower is almost directly due north. It's a 25-minute walk. If it took you 33 minutes this morning, you came by the long route. So we'll find you the shortest route and make sure. It's actually a very nice walk because the first half of it is along a stream, it's wooded, and the second half of it is in campus. So it's a nice walk. However, for the first 2 weeks, we're going to organize a shuttle. You'll get a chance to get picked up at, I think, 8 and 8:30. And then the shuttle will bring you here. So you can use that. Later on in the summer, you're on your own. In the evenings, Hopkins does run a courtesy van, a shuttle. There are about 2 or 3 routes with colors, red, blue, green. And they pick you up just south of here at Mason Hall, and they'll drop you off. And like they go anywhere within a mile of campus on call, and they have fixed routes. And one of the fixed routes does go by Loyola. So you can choose either one, especially if it's late night. I'd recommend taking the shuttle home rather than walking once it's dark. Of course, it gets dark only at 9 p.m., but still, right? So that's that. Commute. Okay, a couple of other logistics. There are a number of you who have come from overseas. Check with Ruth. There might be some visa formalities. You may need to go do an I-9 or something or the other. Make sure you get that done. And you can do it between lectures and labs whenever you have time. And where's this last one? I can't even read my own handwriting. Oh, yes. We showed a set of hands, like, short-term students, 8-week students. One more show of hands, Hopkins students. Okay, everybody turn around and see who they are. So these guys are your local help. If you have any local questions, where is the nearest ATM or whatever, rather than ask you, many of them live around campus. They'll tell you where it is. They'll tell you all other stuff that I don't know. There's apparently a secret grad student handbook somewhere which tells you cheap places to eat and all that, but find out. Okay, so and Hopkins students here, this is both your privilege and your duty. You're local host to all of us. So please help out the other students. They're here only for 8 weeks. That's not a long time to figure out a place. Tell them your favorite places to eat, how to get quickly to downtown. There's a free bus, by the way, and so on and so forth. Right? Okay, and what else? That's it. Any questions, any comments, any jokes? No? All right. In that case, let me stop the introductory remarks and hand the floor over to my colleague, Professor Kevin Du. Kevin, floor is yours. Oh, yes, actually, I walked away with a mic. Should be live. Yeah, thanks.
All right, does this sound okay? Okay, cool. Yeah. Okay, that's good. All right, everyone, good morning. Welcome. My name is Kevin Du. I'm a research scientist at the HLT COE, which is a sister center of CLSP. I'm also affiliated with CLSP and CS here, as many of us are wearing multiple hats at this school. So I'm very happy to welcome you all here. This is very exciting times. I remember actually 20 years ago exactly, I was a student at the NACO JSALT summer workshop. And I had a lot of fun. I actually met a lot of friends that I stayed in touch throughout the years. I also remember playing Frisbee out in the quad over here. So you should definitely have fun while you're here. Okay. All right, so today, just to get started, we have each day is a different topic, as Sanjeev said. And the idea is to make sure we're all sort of on the same page so we can talk more later when the workshop starts. So today I'm going to talk about large language models. The idea is I'm going to go through the basics. I'm sure many of you know about this. Actually, can I get a show of hands? How many of you have heard of large language models before? Right. Of course, right? So actually, how many of you have used large language models in your research in some way? Okay, so actually quite many people. So this tutorial actually might be a little bit simple for some of you, but the way I'm going to do it is this. So I'm just going to talk for about 1 hour on the basics, and just to make sure we're on the same page. Some might be review, some might be interesting new stuff, and I'll try to do as much as possible, put in my own perspective, just to make things interesting. But that also means not everything I say is true. It's just my opinion. So just keep that in mind. So I'll talk to 10:20. After that, we'll have a break. And then I thought it'd be interesting to show you some of the interesting research that's related to large language models. So I invited about 6 people to come give very short research talks on that. So that's until 12. And then you'll go out to lunch. And then I'll start the computer lab at 1:30. But at 1 to 1:30, I think our IT person, Dan, will be at the Malone Hall. So please do come if you need help with computer setup, like if you need Wi-Fi, if you just want to make sure you can log into the computer. So we'll start our lab promptly at 1:30. So just to have some flexibility, if you want to have a long lunch, come at 1:30. But if you want to make sure that all your computers set up, please come before that. Okay? Any questions? All right. So I'm going to start the tutorial. And feel free to interrupt me if you have questions, okay? Or if I say something wrong, which is totally possible. All right, so the goal of this tutorial is first, I just want to have some common terminology that we all use. The way things are is LLMs are really popular. So everyone says I work on LLMs, right? And that might mean everyone's actually talking about different things, right? So would you call BERT an LLM, or would you call say Whisper LLM, right? I think there's just a lot of things out there. And so I just want to establish some common terminology here. And this is a term I will use. It might be different from what your research group will use, and that's fine. Don't make mine a standard terminology, but at least now you have a standard terminology, then you can, when you talk to different groups, you can kind of make the relation. So that's the first goal. And the second goal is I just want to point out some things that we take for granted in this research, and just I'll mark things that we kind of take for granted and think is true with this lightning bolt here. And that means be cautious of it and don't fully believe everything that either I say or the researcher's blog says. So hopefully that will be interesting for people who already know the material. Okay, and here's the outline. So I'll start by talking about why I think LLMs are fundamentally different from all the other things that came before. Okay, and I'll probably make some outrageous statements here, and then I'll talk about second how LLMs are built these days. And after that, we'll do a quick survey of popular implementations, and then finally some advanced topics. And I think a lot of the research groups will actually get into these in more detail. And there's also many of the lectures coming up in the following 2 weeks. They'll also cover some of these things in more detail. Okay. All right. Should we get started? Let's see. So why are LLMs fundamentally different? Now, to do that, first we should define what's an LLM. What do people think? What is called a large language model? What's called a not so large language model? How would you define that? Right. So one definition is size, right? So of course it's called large. So it kind of reminds me of back in the days, people designed circuits, right? there's LSI, and then there's VLSI for very large. What does that even mean? LSI. People remember? Yeah, but anyways, maybe there's going to be ultra large LLMs in the future, right? So is size one of the definitions? Now, then what does it mean to be large, right? Is 10 billion parameters, is that large? Or do you have to be 100 billion? I don't know, right? So I think that was a traditional metric of what defines the LLM, but I think actually that might be going out of fashion, right? You can have very small large language models now. Okay, another definition is architecture, right? Is this decoder-only structure that people use? Is that what defines the large language models? Indeed, that is what defines a language model, but I don't know. There's also training objectives. So we'll talk about this more later, but we can train to predict the next word, or you can also mask out words in a sentence, train to predict those. You can also train to predict, say, the next sentence, things like that, right? I think the truth is these days, anything can be called an LM if it's good for a press release, right? So that seems to be the way things are going now. But here's the definition that I prefer, and I'm going to kind of focus on this in this talk. So I think what defines LM is the intended use. And the intended use is that these are models that are intended to be used for their emergent abilities and also have multiple purpose. So I'll talk about this in more detail later, but that's sort of my definition of what's an LM, okay? Now this could be different from other people, so just take note of that. Okay, so now I'll go through a few things to try to make this definition clear. So there's a language model, a pre-trained language model, and a large language model. So I'm going to make a distinction between them, okay? So I would say a language model is something where the intended use is just to predict the probability of the next word, okay? So that is a language model. A pre-trained language model, something like BERT, I would call a pre-trained language model. The intended use case is a single task after fine-tuning, right? So the idea is you train this model. After you're done training this model, you find the task that you care about, say it's sentiment analysis, then you fine-tune on that data, then you have a sentiment analysis model, right? So intended purpose is a single task, and that's what I call a pre-trained language model. And then finally, the large language model, something like GPT 3.5. Now, the intended use is actually not defined beforehand. It's multi-purpose. So the idea is you put this out, people can use it for anything, and even things that it's not trained on. That's the emergent part, okay? So that's the distinction I'm going to make. By the way, feel free to raise your hand if you object or anything, okay? All right, so now let's just quickly go through these just to make things more concrete, right? So LM, the intended use is to predict the probability of next word. It can be used in many things like speech recognition, where you want the probability of a sentence. This is a sequence of words. You can use a chain rule to decompose it into these conditional probabilities. And then sort of in the old days, when we use n-grams, we take these, this is the probability of, say, the second word given the first word. We would use counts to derive this probability. Whereas now, we would use a neural net to compute this probability, okay? So that's what I call LM. Is the main thing is you want to model this probability, okay? And there's many ways to do it, but basically you try to improve on perplexity. So I think I won't go through. Can I just get a show of hands? How many of you know perplexity? Okay, how many of you are perplexed by this? Okay, all right, so maybe I won't go through it, but just know that almost all the time in the language model, we're trained to minimize perplexity, right? And you can go through these slides later, or I'm happy to talk offline too if you don't know this, okay? All right, so here's an example of a neural network-based LM, where you have vectors representing different words, and then you put it through some layers, and then finally, you have output nodes that basically represent the probability of the next word. Okay, all right, so that should all be clear. Now, what is a pre-trained language model? And I'm going to define it as fine-tuning for one task. So the intuition is that if your pre-training is trained on large enough data, you can have a good representation. And by having a good representation, then you can adapt to a task much quicker. Okay, so for example, if you have a BERT model, you train this BERT model on the LLM objective like perplexity, but you might also do other objectives too. You get that model, and then you fine tune it, means you run supervised training more on the task you care about, and then you can deploy it on that task. Now, if you have a different model, different data, you can fine tune on that data, and then you get a different model. Okay, so here the idea is if you have 100 different tasks you care about, in the end, you have 100 different models. Okay, so that's my definition of a pre-trained language model, is this model here that allows itself to be fine-tuned for different tasks. But once it's fine-tuned, it's really for that task. Okay. So now let's move to then what do I call large language models. And I think this is sort of where things got a little bit strange for me. So when BERT came out, people were very excited. It's used for every single NLP task out there, and has great performance. But then later, GPT-3 came out, and it's pretty much the same architecture, but just trained on more data. But then suddenly it can do much more, right? You can tell it to do math. You can tell it to do coding, right? Those aren't things that you would expect BERT to do, right? For BERT, you would say, I give you this supervised data, fine-tune it, and then you can do it. But somehow GPT-3 and GPT-4, somehow they claim that once you scale up the fine-tune, once you scale up the pre-training on large enough data, suddenly you can do something else, right? So I think we should pause a bit on this. It's actually a really crazy thing, right? Like we're kind of getting something for free, right? Doing this. So let me discuss this a bit more. So emergent abilities, what I mean by that, right? So somehow when you train on more data or when you have larger models, suddenly you can do something else. So the way to measure this is something like this. So here I have a quote from a physicist. Emergence is when quantitative changes in the system result in qualitative changes in behavior. So think of it as a phase shift. Suddenly something happens. So here's the phase shift. So this is amount of, think of it as amount of data times amount of compute. So that's basically the amount of iterations you go through. So the training flops, the larger you go, that means the more machines you're using, the more data you're using. And this is measuring accuracy on some task. So here, this is some kind of arithmetic task. Oh, I forgot to write where this paper is from. It's from I think it's from a Facebook paper. Oh, okay, here. So yeah. So if you want more details, I try to put in the papers so you can search more if you're interested. Okay, so what's going on is here you see 0 accuracy for different amount of training budget. And then suddenly at this point, you have non-zero accuracy. So this is GPT-3 model. This is another large language model called Lambda. And that's sort of the crazy thing that happens. Why in the world will you go suddenly from 0 accuracy to something? Right. Similarly here, this is a transliteration task. You have 0 accuracy, and then suddenly you have some non-zero accuracy, right? It's the exact same model, exact same training objective, but just more compute. Okay. And so basically another way to phrase it, and this paper says, well, is an ability is emergent if it's not present in smaller models, but it's present in larger models. So in a sense, they're defining large language models by size, right? But I think more so than size, it should be defined in terms of this emergent behavior. Okay. Any questions, comments? Yeah, go ahead.
So, I mean, the x-axis is on a log scale, but right at the y-axis is on a linear scale. I'm just curious, at least in physics, oftentimes when you think about phase transitions, there's actually a break in the scaling relations, right? You
Okay.
sort of have a different exponent. So if you put that on a log-log plot, I'm curious, is there actually a break there? I mean, apparent in the linear, but maybe it's just an exponential.
Okay, yeah, that's a good point. I don't know. So if you, yeah, so yeah, I think if it looks like that, there will be some changes, right? Maybe we should look at that in more detail, right? Like these are not physicists doing the research, but maybe we can get more ideas from physicists. Yeah, good point. Mhm. Okay, other comments? Yeah, go ahead. Okay, I see. Oh, actually, I'm told to repeat the question. So the question previously saying that physicists they look at this is a log scale and this is not a log scale. Usually they look at log plots, right? And then emergent behavior is when there's a sort of a change in the exponent. So the question was, is there such a thing there? And I didn't know. Okay, all right, go ahead.
You define ability, or how do we alter some?
Okay, how do I?
Because maybe for some 30% interest.
Yeah, that's a good point. So how do I define ability, right? So here we're just saying ability is something that goes from zero accuracy to non-zero accuracy. Although you can imagine this is actually not that high, right? Yeah, maybe I need to define a threshold. You're right. Yeah. I mean, it's a bit hand wavy, right? So maybe this is actually not 0, but 0.1, right? So do I say there's a phase shift or not? You're right. There is a threshold that we need to define. Okay. Other points? Okay, that's good. Yeah, let's be as interactive as we can. That's good. Okay, so that's emergent abilities. I'll show an example of an emergent ability, and this is something that really Hello? Can you hear? Can you hear? No?
Probably take it all for YouTube to catch up, but can I keep talking with
Okay. Yeah.
saying something to get the
All right. Does someone have a joke they can use at this point? All right. No audio still? Should I change?
Oh, so, yeah, okay. I think there might be one other. Yeah, so you need to switch yourself out.
All right. Hello, can you hear me? Okay. Can you hear me now? No? This is the internet connection.
Backup button.
All right.
All right, so this will be this mic.
Okay, so I just stay
it'll
here.
just be closer.
Okay.
And then we'll figure this out during the break.
All right. Okay. So hopefully people online can hear me now. All right. So we talked about emergence, and I think this is sort of one of the defining things about large language models. Why do they emerge? People don't know. Is it really because it's trained on more data? Is it because of over parameterization of the models? Is it because you're training on code or training on instruction? Is it because of this reinforcement learning thing? Or is it because some magic? I don't know. So this is an interesting blog post that tries to decompose different possibilities, but I think people still know why these things emerge. Okay. So just to kind of push this point even further, I think, okay.
Yeah, could you tell us more about what people are thinking?
So for example, why does chain of thought prompting work? So for a while, people floated the hypothesis is because GPT 3.5 had some code in their training data and ideas that you become more logical once you train on code. But I think it's actually it's a jump, right? You kind of, people believed it for a bit, but I think it really is not. If you think closely, just training on code as raw text doesn't mean necessarily that you become more logical, right? So that's one thing. For RLHF, so I think OpenAI stressed the importance of RLHF in their first announcement of ChatGPT, right? So they have humans rating things, and they say that was important. But then later, it seemed other people were saying maybe it's not that important, and then people have done reinforcement learning without really using that many people to do the feedback. So it's really not clear. Yeah. Any other questions or comments about this? Okay. All right. So I just want to kind of put on my old guy hat and be skeptical of all this, right? So when I first was reluctant to enter this field, actually, it was a student who pushed me to join this. But I thought it doesn't make any sense, right? So first, back in the days when I took Machine Learning 101, I learned about this no free lunch theorem, right? Which says that if some machine learning method works well on a certain class of problems, it must be paying degraded performance on other problems, right? There's no free lunch in the world. But LLMs seem to imply there's free lunch, right? You have a single model that can do everything and beat everyone else, right? So that seems to go against this free lunch theorem idea. Although actually, to be honest though, this no free lunch theorem has actually very specific assumptions which actually don't apply in practice. But still, I think intuitively, it makes sense that there should be no method that's good at everything. And the other is more from a math or optimization perspective. if you think of when you do machine learning, you have an objective function, and then you minimize that objective function. So in our case, it's perplexity. Now, there is theory that says, okay, if you assume that this objective function represents what you really care about, which is the test generation error, there's some way to bound things, right? Let's say if you assume you have a smooth class of functions, you can assume the world is smooth. If you minimize on the training set, then you can also have some guaranteed generalization on the test set, right? But this is all based on you optimize this objective function, right? But in this large language models, the objective function we're optimizing has nothing to do with the objective function that we're using it for, right? So this also doesn't apply, right? So I think these are two things from Machine Learning 101 that sort of says, hey, why would large language models ever work? Okay. All right. So now I'll give a few explanations on why large language models might work. These are just some things that people have proposed. Now to do that, first I should introduce scaling laws. So this is from Jared Kaplan, who's actually a professor here, but he worked at OpenAI and now he's at Anthropic. So he and a couple of the whole team, they proposed this thing called the scaling laws. And this idea that language model performance improves smoothly as we increase the amount of model, data, and compute. And those are sort of the three things that matter: compute, model, data, and compute, right? So you see plots like this. As you increase the amount of compute, your perplexity goes down. And all these lines are different models that have been trained, okay? So different models, think of it as their learning curves. And this is plotting out sort of just a continuous decrease in this test loss. Similarly, if you have more data, you have this behavior, and then more model size, larger number of parameters also have this behavior, okay? So here's sort of the first part of the explanation is when you have a larger model, you can sort of arbitrarily improve the perplexity. And now the second question becomes, okay, if you arbitrarily improve the perplexity, why does it have emergent ability, right? So this is the second part. So here's something that I think kind of makes some sense, but I put a lightning bolt here because it's still not sure if it's true. If you think of a next word prediction task, it's actually a massively multilingual, a multitask problem. Was there a point there? Yeah.
Models, like, what do you mean on like batch size?
Compute, what I mean by compute?
Yeah.
Okay.
Batch size.
Okay. So I mean, okay, maybe I'm going through this a bit fast. So by compute, they define compute as basically flops that you use on the GPU when you're training, right? So, and these are related, right? Think of it, each backprop iteration, how much compute you use depends on your batch size and the number of parameters in your model, right? So the bigger the model you have, each iteration, the more compute you're using, right? So actually these three things are interrelated, right? You can have larger data and smaller parameter, but that will result in smaller compute, right? Or you can have larger parameter and smaller data, result in also less compute, right? So they're kind of all related in that way. But I think what this paper was showing is that sort of they all matter, and you can kind of trade off, right? So if you have smaller model, right? Say your RAM is not big, right? You only have cheap GPUs, right? So you have smaller model, but maybe you can run it for longer, pay more compute, and you can get the same performance as someone who has a bigger model, and could just run fewer compute. So hopefully that answers your question. Okay.
Okay, just to emphasize the answer, the x-axis on that is petaflop base.
Yes, petaflop days is the x-axis. Yeah.
Times 1 to 1 day. So
Yeah.
10, like 1 in that is like 10 to the 20. Floating point.
Yeah, yeah. Yeah. Right. Okay. All right. So I'm saying this, you can imagine next word prediction is a massively multitask problem. So say we're trying to predict the next word in this article, right? So Johns Hopkins is a name. You have a time here, right? You have some words that require syntax knowledge. When you see the word Baltimore, comma, you kind of know the next word is Maryland, right? That's a geography knowledge. Words like heavily, right? This adverb comes near this verb. Also this Baltimore in Ohio, if you know about the history, you know this is not about a place. This is a railroad company that connects these two places. There's also things like NAFRA, right? So he refers to who? Refers to Hopkins. So basically the idea is that if you want to make the model predict the next word, well, the model kind of needs to know all these things, right? So it needs to know what's a name. It needs to know about geography. It needs to know about time. Right? For example, maybe how do you know it's 1873 here, right? You know that 1873 comes after 1795, right? But these are all knowledge that we have, and maybe by forcing the model to do this, it is actually learning all these things about the world. And because you can arbitrarily reduce perplexity, then the model can afford to learn these things. So that's sort of a one explanation, right? Now, in the old days, when we have smaller models and we're training the model to optimize perplexity, it really didn't have the capacity to learn all of this, right? Because it's a smaller model. So it had to sacrifice on these long tail kind of things. But then now with these humongous models, we can maybe force it to do everything correctly, right? So that's one possible explanation on why large language models can be multi-purpose and be emergent. It's because this link between this next word prediction task and all the other tasks in the world. Okay, so that's one hypothesis. I mean, I wouldn't say it's true, but I think it's reasonable. Okay. Any comments or questions? All right. Now, so that's about just general, how does the large language model know so much? This is more specific on how does the model do in context learning, right? So there's some hypotheses out there. Some people say maybe by giving it some examples, it's identifying the task you want. So this paper explanation of the context learning as implicit Bayesian inference is pretty, I recommend reading it if you're interested. Okay. There's also people saying that, okay, that might work, but you want to make sure your pre-training and fine-tuning has enough task diversity for this to happen. So that's one camp. Another camp, this is very interesting. So they're trying to think of the neural network and ask, is there, so in context learning, the main thing is there's no gradient updates and somehow it can do a new task. So you're trying to figure out from the structure of neural net, say this attention network, is there anything with it that is basically like gradient descent, right? So you can do forward pass, but it's actually running gradient descent in the forward pass, right? So these kind of papers try to explain it from a architecture perspective. And then there's also papers that talk, maybe there's both going on. And actually, if you look at, I think nowadays when people look at large language models, they have a whole large benchmark and they just average the scores. But when you actually look at for each task, the performance varies a lot. So this paper is trying to say maybe both things are at work, depending on the task. Okay. Yeah, so That's this paper in more detail. I think I'll just mention this because I think this is an interesting experiment, and it kind of points at some things that academics can do that still has an impact in this age of large language models. So they're trying to figure out, okay, why do the in-context examples work? And the way they did it is they give us some in-context examples, and then they try to swap things. So say you give it this sentence, and then this is a label, it should be positive, this is sentiment. And then you can kind of corrupt the labels, right? You can scramble them. So basically they did different kinds of corruption and see if in-context learning still works. And they have some interesting results kind of pointing that it seemed like actually having the labels didn't matter. They could give it random labels and still somehow it did something. Okay. All right. Now, I think that's the end of this part. So I just want to end by this sort of personal perspective. So I think the way we do research has changed a bit since large language models came out. In the past, what we would do is we would have some idea, and then we think carefully about, does this idea match our intuition? Say, I want to put syntax into machine translation. Say I want to put a certain type of syntax, like I think morphology matters for translation, right? Then I think, okay, does it really matter, right? What's the linguistics behind it, or what's the machine learning behind it? And if it makes sense, then I will go ahead and implement it. If not, then I'll generate a different idea, right? But now I think because large language models can do so much, and people kind of believe that they are emergent, they can do multiple things. What people do now a lot is you have some idea, and you just assume the language model component can handle it, and then you just do it, right? So you kind of run this loop. You don't have this sanity check phase before implementing something, because you assume that large language models can do everything. So that's sort of, I feel like sometimes we are in this approach. I'm not saying it's good or bad, but just want to point it out, right? Maybe you do things faster here, you're more courageous, right? Whereas in the past, if you have an idea that doesn't make sense, the advisor will say that doesn't make sense, don't try it. But now you just try it anyways, right? But it could also mean that you're kind of doing things that aren't really working, and it's because it's assumption that large language models can do it that might be false. Okay, just something to keep in mind. All right. All right, so that's the end of this first part. Are there any questions or comments? Do people need a break? All right, who needs a break? All right. How about let's take a 2-minute break? You said 5 minutes?
Yeah.
5 minutes? You want 5 minutes? Yeah. Okay, 5 minutes. So let's come back at 10 o'clock.
Yeah.
All right, it's 4 minutes.
Yeah, okay, let's try it. Okay, let's try. It has a very faint
Hello?
signal.
Okay.
It looks like it's.
Yeah, Is it working? Can you hear me? Can you hear me?
We're seeing the mic icon.
Hola. Hola, Paula. Can you hear me?
No, you gotta go to the Zoom.
Oh, so this is Zoom, right?
Oh, I'm sorry.
Thanks for coming.
I didn't need a break.
Feel free to run after you talk. Okay. All right. Hello, can you hear me? No? Yes? Hello. Sound check. You can hear me? You can hear Sanjeev? Okay. But you can't hear me? Maybe it's coming from something else. Oh, it's working? Okay. So just a delay. Now it works? Now it works? Okay. Okay. All right. So we're good.
And then I don't know how many breaks you guys have, but I would turn it on and off in between each one because they only have a few hour life.
Okay. Was that the problem that it's running out of battery?
It could have been, there's a second one that they're charging in the back. Next time if that happens, I would just tone. I asked one of my colleagues to come down here, though, who's more familiar with mics
Mhm.
to check out.
Okay.
I will say join Zoom. It sounds like
Okay.
it's working.
Okay. Now I just need to untangle this.
How long are you guys on? Again?
So we'll start at 10 o'clock. So basically now. Yeah, and then we'll have break at 10:20. And that'll be a long break. I might go a little bit over.
Okay. Yeah, I'm gonna step out and call signal really bad and let them know that 10:20.
And now you actually like confirmed it, so I think
Sorry for asking. Oh, no, it's
Random question there.
No, it's good.
Actually, I do think when you showed Derek Kaplan's paper, like that seems to indicate that at least, whatever
Yeah,
domain they
it's
trained,
yeah.
that there's a single scale, like maybe just our perception of what we call emergence, appears because we're like, well, if this thing is getting 0. If
I
it's
see.
getting like a 0.0001 percent accuracy versus 0.01 accuracy, or even 0.1% accuracy.
Yeah.
If it's less than 1% accuracy, we just say this thing is at all.
Yeah.
But maybe, if you look at log word probability or token probability or
Yeah, but
complexity or whatever.
Jared's stuff is all on perplexity.
Yeah,
So
okay.
I think the emergent stuff is not perplexity, it's
Right.
some other task.
Other
So it seems like what people are saying is perplexity has this
Right.
log,
Signals.
this single exponent for the perplexity.
But
that-
the emergence appears on the other.
yeah, yeah.
Yeah, I'm curious if. The physicist in me is always interested in like scaling laws, which is probably why Jared wrote that career, because he was from the physics department.
Yeah.
Yeah, so.
I think we need more people from outside to make sure
I mean,
we're doing the right thing.
it's good stuff. I appreciate that.
Mhm.
Definitely, I definitely learned a lot.
Cool.
So, yeah.
All right. All right, let's get started again. All right, so how are models built? These are the basic steps involved in building a large language model. So first you have data preparation. And this is where you collect all the raw text you want to train the data on. And this is actually a very important but much underappreciated task. I think people like the fancy machine learning stuff, but actually this is really important. And if you go through a lot of the papers that these big companies have and look at the authors, sometimes they divide by the teams, and you can see this team is actually humongous. right, in order to do the data. Now, once you have the data, you have the pre-training team. And so they focus on picking the architecture. Sometimes they will try things on the smaller architecture to see how things go. People often use the scaling law to predict what should be the real size I want to try. There's also a lot of grid infrastructure stuff that's important when you're doing the pre-training. So often people train on massive scale, which means not a single GPU can fit the model. So you have to do model sharding as well as data sharding. So that's the pre-training step. After you have that, optionally, you might want to fine tune. People call it alignment sometimes. But basically, you have some supervised data in some form, and you improve the parameters a bit more. And usually that's the end of the large language model. So you release it here. And then if you have other users, they might additionally fine tune on the language model that you release. Right, so this is how I divide up the main stages, 4 stages, basically: data, pre-training, fine-tuning, alignment. So I'm kind of putting, some people put the RLHF as a separate thing. I'm just putting it together with this fine-tuning step. And then finally, this downstream fine-tuning step, which is done by different people. Okay. So now I go through each of these in slightly more detail. So data preparation, this is very important. Andrew Ng had this quote. He said, perhaps it's time to hold the code fix and invite researchers to improve the data. He said this 3 years ago. I don't know if it's happened much yet. There are papers out there now that are trying to do this. But I think in general, it is hard. We kind of need a change of our sort of perception of what's hot in research. Okay, now what are the questions that are important here? So these are kind of things that are important. So what's the optimal mix of data sources? You want some code, you want some different languages. Actually, the mix is very important. And it's actually not clear how to find the optimal mix. What kind of data cleaning? This is very important, especially if you care about toxic content or content that shouldn't be out there. Cleaning is very important. And then tokenization also is something that people don't think much about. I think, for example, the newest GPT that came out, actually the tokenizer, that is a big deal. It runs way faster. There's certain things that it does that's different from before, and that could actually be important for its actual improvement. But it's hard to know when you're implementing these things, what's the most important thing and how much effort you should put. Because all these are decisions you make early on, and then finally you train a single model. You can never go back and revisit these. Yeah, but these are important. So here's an example from Salesforce. So Shafiq Jyoti from Salesforce, he came to CSP last month, and he gave a talk on their LLMs. And this is sort of the data sets, the mixture that they're using. And you can tell that there's a variety of data, and the sampling proportion you want to use for each data set, that requires some thought to figure out what's the right sampling proportion. They actually use a 2-stage setup. First, train on language, and then the second stage, they put in some code data. Right? So again, these are decisions that you need to make when you're trying to build a data set. So a lot of the CSP talks are online. If you're interested, I recommend you go to this. If you go to the CSP webpage, you should be able to find it. Here's another example of what's important in data is filtering. Right, so this is from this paper that built Falcon LM. And you talk about different things they need to do. So just to show kind of things you want to do, URL filtering, extract the text, you need to find the right language. There's a lot of repetitions on the web, so you need to remove those. And then this is not even including any of the toxic content detection stuff, right? So you see they go from this amount of data to something that's much smaller. And all this requires a lot of work to get done. Okay. last but not least, I recommend this paper. It's coming out at NACO next week, actually. So they had a very good, so this is from a company. They had a lot of resources to test out different kinds of things that matter in pre-training. So look at things like toxicity, domain coverage, the age of the data apparently matters a lot. So some of the findings they said, for example, temporal shift between the evaluation data and the pre-training data leads to performance degradation, which cannot be overcome by fine-tuning, right? That's actually kind of interesting statement. That means you need to train your large language models much more frequently, right? And that's a scary concept. Yeah, so I recommend this paper if you're interested. Okay, any question?
First been trying to like filter out text created by other large language models when
Very good point. Yeah. Yeah. Is there anything on trying to fill out text created by other large language models? I'm sure people are doing that. Yeah, that's important. You don't want to train on that data. Good.
On the other hand, there are some, especially like vision language models, that are using explicitly output from GPT-4
That's true.
as like in like a pseudo teacher.
Yeah. Okay. Yeah. So another comment was there's some work that use large language model to generate pseudo data to train. Yeah. Yeah. But I think the way to think about it is if you should filter out machine data from the raw data. But if you want to have synthetic data, you create it. But in that case, you know exactly what it is, right? So I think that's an important point. Okay, very good question. Yeah, go ahead.
Synthetic data, I believe a lot of the big tech companies are on purpose training their models on synthetic data because they're running out of actual internet data.
Okay, okay. Yeah, so the comment is maybe the companies are training on synthetic data because they're running out of real data. Yeah. Okay. Yeah, go ahead. Okay, is bias considered part of toxic content? I think, I don't know. I think it is, but I feel like we don't have a standard terminology for that. Yeah, but I think in this paper, they do look at bias, I think. Yeah. Okay, questions, anything else? All right. Now second is architectures. So now you're done with data preparation. You want to start training a model. First thing is you decide what kind of architecture you use. So this picture just shows you can have an encoder decoder model. You can have an encoder only model. You can have a decoder only model. Decoder only model is pretty much standard now. And also people are going for larger context windows as the input. There's also some new innovations. So besides transformers, mixture of experts seems to be catching on a little bit. There's something called state space models that people are talking about too. Okay. All right, so I won't go through details here. Now, in terms of models, I think the number of parameters does matter a lot. So you have to think about how this matters for training as well as inference, right? So I think I roughly divide these models out there in 4 categories. This is just from my academic perspective. So you have models less than 1 billion parameters. That's something that's easily done and might not have these emergent abilities. And then you have these 1 to 10 billion models, billion parameter models. Academics can use this in their usual GPU setups well. And then things get larger, 10 to 100 billion, and then also the greater than 100 billion models. So now how does the model size impact, how does the number of parameters impact model size and inference? You can roughly think of it as, right, you have a single parameter, usually 4 bytes to store that number, right? So if you have 3 billion parameters, you have 12 gigabytes on disk. So that's just the file. Now in practice, people can get away with 2 bytes per parameters, right, using floating point 16, right? So so maybe a 70 billion model is 140 gigs on disk, right? So if you think of this, 140 billion gigs on disk, we could load it into a academic system with, say, 4 GPUs, right, on a single machine. Now, impact on training, you need more when you train. So rough guide, you need sort of 6 times the number of bytes to do optimizer state gradient and temporary stuff, right? Because you need to do forward and backward, and you need to store extra stuff, right? So maybe if you have a 3 billion model, you actually need 72 gig for RAM on the GPU, right? So that's sort of that's why we can do these kind of models in our GPUs, but maybe if you want to do more than that, then you have to actually go multi-node. Okay. Yeah, I think that's all I wanted to say here. Just a note about the multi-node stuff. So single node multi-GPU, I think a lot of us can do it, but multi-node multi-GPU, that's a whole different beast. I think it requires very fast interconnects between different nodes, and you have to be prepared if you actually want to do that. Okay. All right. So now what about the cost? So here are just some things I took out from the literature. So for example, the 70 billion model of Llama, they said they trained on 6,000 GPUs for 12 days on 22 terabytes of tokens. And then in the end, it's $2 million for them. Okay. There's this Salesforce paper. So they trained on less data. For them, it costs 150K. So that's actually doable. So you can see there's actually a large variety of things out there. Some people have models like this that just there's no way anyone can reproduce. But then also some people are showing models that actually different groups can do on their own. Okay. So I don't know if any of the groups here are going to train a large language model this summer, but you can do it if you want this. Okay. All right. Any questions on pre-training? All right. Okay, now I jump to the next step, which I just lumped together: fine-tuning, instruction tuning, or alignment. I'm just going to call everything fine-tuning. Some people like to use the word alignment, saying that in this stage, they're aligning the model to human values. Personally, I don't like that word. I think it's sort of making things too high level, right? Like, we're not really aligning things to human values. We're just aligning things to the labels that represent someone's perception of what's right or wrong. But anyways, some people use the word alignment for that. Yeah, so why is this helpful? This can help you specialize. It can help you learn to chat. So ChatGPT really relies a lot on this stage. It might also be helpful to make the model get used to the prompts that you give. So after you train on the next word prediction, later you want to use prompts for the models. The format of the prompt is important, and this might be helpful. Yeah, question? Human, by human value, do I mean human quality or what humans would produce? So I think people use it in a hand-wavy way. So it's really what humans produce. But some people say, well, and that aligns with the value of humans. Right? I don't know. Human quality, it depends on exactly how you're doing. So I think since I'm lumping together a lot of things in this, so some people use, say, real data from humans, right? It's like if you think reinforcement learning, you actually have a human feedback, but then some later people actually trained the feedback model from human data. So then it's actually a computer generated feedback, right? So then it gets iffy what exactly counts as human or not. Yeah. Okay, anything else? All right. So now this is an example of instruction tuning. So for example, this is a language model, and you give it summarization data. You give it sentiment analysis data. These are the outputs of these data. And basically, you give it to the model. This is after pre-training. You fine-tune on this data. And the idea is that will make it more amenable to other kinds of tasks afterwards. Okay. This is a reinforcement. I'll skip this part for time. Okay. All right. Maybe I should talk about this. Okay, I will talk about this because I think some people will use this in their research. Okay, so I think up to here, you can imagine that the data you have is sort of in the supervised form. So you have the input and you have the output. Whereas here, you can have data in comparison form. So you can have basically, you ask the large language model to generate two outputs, and then you ask which one is better, and then use that as a signal to train. So that's the whole idea here. Whether that signal is provided by an actual human or a model, that's a separate point. But there's a lot of research on this, on making it more efficient, things like that. Okay. All right. And then finally, this is something that people might use. Once you have the large language model fixed, maybe you want to use it for your own task. You can do something called parameter efficient fine-tuning. And this actually is a whole set of techniques. One example is this thing called LoRa, where this is one of the layers of your model. You have the pre-trained weights, you keep it fixed. And then you add in another set of weights. So this is a low rank set of weights here. Rank is the R here. And the idea is that, say you might have a 70 billion model and you can't afford to retrain on those 70 billion parameters, but you can train, say, 100 million parameters with this extra component that's inserted into your model, and then that could do well in your task. Okay, so I imagine some people might use this for the research. All right. Okay, so maybe just this one slide to end this. So there's many models out there, and they're kind of all at different stages. And I just want to show this picture so people keep things clear, right? So say you have Bloomberg released this thing called the Bloomberg GPT. They want it to work for financial news. So what did they do? They start all the way from data preparation, and they did their own pre-training. So it represents a model that covers these two components. You might also have Llama that's converted into Astrollama. Maybe you'll hear about this in one of the research groups, right? So the way they did it is they train on specialized data. So basically also these two components. But you also have many things like Vicuna. They take Llama model, and then they did fine-tuning on top of that. And that fine-tuning data was generated by ChatGPT. But that basically represents just using this part, right? And then finally, you have models that just take what people have done and then just do the downstream fine-tuning. And Shen will talk about this later in one of the talks. Okay, so these are sort of different ways. And you can imagine people have all sorts of different models out there now. The family lineage of that model actually becomes important, right? So there's all these names, but actually they all derive from some place. Okay. All right, any questions or comments? Cool. So I realize this is the end of my time and I've only covered half of my slides. So what do people want to do? we can end here, or we can reduce your break time. Or we can do some of this at the lab if you want. I can cover it briefly. I don't know, what do people prefer? What are your suggestions? Okay, so how about let's have a vote? So 3 choices. One is I've had enough of Kevin, this and this. All right, that's the first one. Second is let's reduce the break time a little bit and just cover a bit more. And the third is let's still have our break, but do a little bit of this at the lab this afternoon. And unfortunately, the online folks won't be able to get it, I guess. But yeah, but maybe have a vote here. Who wants, okay, no more of this? We can end here. And oh, the slides will be available. So actually you can read it yourself, and I'm happy to talk to you after. So who wants to just end it here? Okay. I won't feel hurt if you say it, so feel free to raise your hand. All right, now who wants to cut break time a little bit? Okay. All right, then who wants to do this during the lab? Okay, so I guess the break time people won. So how about this? Okay, yeah, that's fine. So when is break until? 10:40? Okay. All right, so I think I'll just do 10 more minutes. Yeah. All right. Okay, so I'll go through this quickly just so you have a rough idea, and then I'm happy to talk offline if you want to talk more. Okay. All right, so survey of popular LLM implementations. Here's a very nice paper by sort of a multi-affiliation group. I recommend it a lot. But they have this nice picture of, okay, you look at all the different models where they're coming from, right? And I think it kind of summarizes a lot of what's going on in the field. So you have the GPT family of models, you have the Llama family of models, and then the Palm family of models. And of course, there's also a lot of other ones that don't fit into this lineage. Okay. And I think I'll skip these kind of things. So I was meaning to talk about a few different models that I think are very interesting, but I think some of the other groups will talk about this. So yeah. Okay. Maybe I'll just mention it. So Bloom is one model that I thought was very well done. This was done by sort of an open community where people got together. If you look at the paper, it's a very long author list. But sort of opens the question of going forward, do we want open access models, or do we work on the models provided by the companies? And I think there are trade-offs, but it's something that we need to grapple with going forward. Okay. All right. So now I'll just quickly sample some topics that I think are interesting. You can think of this as sort of a research problems that someone might want to focus on. So going forward, what are some things that people are looking at? One is smaller models, right? So these models are very big to use either, and if you think about it, pre-training cost seems large, but if you really project how the future will go, a lot of people are going to start using these models, right? You have non-CS people using these models. You have banks using the model. You have sort of anyone out there using the model. I found out recently my neighbor is playing with ChatGPT, right? And he's not even in this field, right? So everyone is using these models. So inference cost is actually going to become a big factor. And you can kind of see this is playing out in the field now, right? For example, Intel is getting into the game, right? They're not doing the GPUs for training, but they're trying to focus on inference costs. So one of that is to give smaller models. You can do something called distillation, but there's also many other kinds of techniques out there. Now, the question is, say you distill a large model to a small model. It's actually not clear, does the imaginability still stay there, right? People don't know. a relay one is efficient inference and serving. So this is a interesting plot from this paper. So when you're serving a model on your GPU during inference time, about 65% of the parameters are actually the model's parameters. But another 30% is the cache that's necessary when you're doing key value computations with the attention model. So now this is something that needs to be recomputed again and again for your input, right? So this actually affects how you batch your model. And if you can have a way to make this more efficient, you can serve much faster, right? So that's one open research question is, this is really getting at the hardware details, or not necessarily hardware, but you can think of it as SysML, systems machine learning. Okay. Better prompts, this is something that is catching on. So a lot of people are trying, so prompt engineering has been popular. It's now a job title, but also there's ways to make your prompts automatically better, right? So here's an example. So say I tell the LLM to say, please write code to do X, right? So, and then generate some code for me here. What I can do is I can copy and paste this code and then put in another prompt. So below is the code that does X. Please fix the bugs, right? And then it actually fixes the bugs. Maybe it fixes. So this is something called reflection. I mean, it's a fancy word, but it's saying that you can sort of call the large language model multiple times and use it to improve itself. And it kind of gets at this idea of an orchestration of large language model. And I think this will come up in some of the other research groups is assume this language model black box, but assume that you have multiple language models or multiple calls to the same language model. What can you do? Can you make things better that way? Some people like to call this system 2 thinking. I actually don't like this word. I think it's too human-like. But it sort of gets at this system 1 thinking is your sort of reflexive, whereas system 2 is your very introspective of where you're thinking. Okay. There's also a lot of work on using external knowledge. So for example, retrieval augmented generation or RAG, that's something that I think some of you will use here. And here the idea is, say I have a question, here's a query, and I could just give it to the LLM, but rather than doing that, first I send this query to some kind of web retrieval to retrieve relevant documents. Then I could put in the relevant documents back as part of the prompt, and then that might improve the result. Okay. Now this is getting a lot of attention. I think one is because it's a nice idea, but also secondly, it's practical. So a lot of groups out there, you can't train or fine tune your models, but you can make the model do something that's relevant to your own task by this approach, right? By this retrieval approach. Okay. And going further, people also use external tools. So this tool former paper is pretty famous. You can generate outputs like this. So the output will say, okay, I generate a sentence, but then at this part, I actually want to call an external tool for question answering, right? Or here, I'm generating this, and I actually want to call it external calculator to do it. So rather than having the language model generate the number, I have it sent to a calculator, right? And this sort of combining symbolic from neural approaches, I think it's a very exciting feature. Now going a bit further is agents. So agent workflows, that seem to be the next hot thing that some people are betting on. So here the idea is that the element is not just generating words, not just generating calls to external tools. It's actually doing the whole task planning and actually like a real AI system. Right? So here's the example. This Hugging GPT paper is recommended if you want to get into this. So say a user says, please generate an image where a girl is reading a book and her pose is the same as the boy in the image that's provided. Then please describe the new image with your voice, right? So this is the input, and this is the output here. And now to go from here to here, you need to first do pose determination, right? And then you need to generate the image. And then you need to do voice synthesis, right? So all these things, the LM can try to figure out, okay, what are the different tasks? And here the interesting thing for this paper is the paper basically makes the LM look at all the different models on Hugging Face. And they are all external tools that can be used. Metadata about those models can be used to define whether to select that model for this and be executed, right? So it's kind of, the LLM is doing all these. It's not just generating next word. Okay. And then finally, you can push this to multiple agents, right? So you can have multiple agents that talk to each other. They're just different LLMs. So maybe in this example, you have the person asking, please plot the chart of the stock price of Meta and Tesla. So you have one LM that's focused on generating code, but then another LM that's focused on interfacing with that. So it's kind of a programming assistant, right? So maybe they're trained slightly differently, and they basically talk to each other and in the end generate something. If you haven't seen this video from GPT-4o, is kind of interesting. They have two GPTs talking to each other. One has the camera, the other doesn't, and see how things go. Okay, so that seems to be one thing that's getting popular is sort of having LMs as agents. Okay. All right, so I think, oh, and finally, this is important, but I don't have time to talk about it. So I think we kind of have a larger responsibility these days to make sure that all the models we build satisfy these criteria, and it's something that we all have to study a bit more, I think. Okay, all right, so I think that's basically all I have. I should let people take a break. Are there any quick questions before or comments? Okay, all right, so now let's take a break until 10:40, and at 10:40 we'll have the research talks. Okay. All right. So five minutes.
So, the microphones are okay? No.
God for this MX. Check 1 2. Check 1 2. Yeah, it's working fine.
Okay. Any troubleshooting tips you could give them? Like if that happened, we can just switch to the other one.
Reboot. Honestly, unplug, plug back in. And if there are any significant problems, so long as the presenter is presenting from the podium,
just switch it back over to the MXL if needed. Yeah, to this one. So, yes.
Yeah.
Yeah. If it at all becomes a problem, swap to the MXL. The MXL should be more than enough to capture anyone speaking within a solid 6-8 feet here. It should be more than enough. A handheld, yes. Unfortunately, ma'am, this is not a space that CLDT controls.
About like Kit Kats,
yeah.
they just don't.
We
Oh,
can't. No, we're whiting. Yes. No.
Sorry. He's really.
I'd suggest that if there is somebody in room, a student or a trusted member of faculty that can just keep ears on the. But then, as long as somebody has ears on it and somebody can hear what's going to Zoom and it sounds good enough, I would keep it on as you have. And if there are any problems, just immediately switch over to the tabletop mic. And you should be completely fine for the rest of forever.
Okay.
Yes.
Okay,
However, once again, the tabletop mic has a limited range, and yeah, that's the only asterisk.
Cool.
Yes.
Yes.
As set as we can be. I left my kid up there, right? My backpack. Okay, cool.
Okay.
Yes. All right.
All we have is.
Lapels like this?
Yeah.
Or okay.
Sure.
Yeah. If I don't have the receiver, I can't.
They don't have like the handheld mic.
Unfortunately, we don't have any that we can loan out. They've all been portioned for other events or.
Okay. That's okay.
Yes.
Well, we can survive with this. Cool. Okay.
Oh.
Okay, I'll hand it. Okay. All right. Can you hear me? It works. Okay. It works. Hello. All right, we're about to get started. Okay, so what we're going to do now is I invited a couple people here to give sort of short. Thanks. All right, so I invited a couple people local to show their LLM research, an idea is to give you a flavor of what the sort of wonderful, diverse things you can do in this space. So first is Reno Krids. Reno is a researcher at the HLT COE, where I'm also from. And he's actually leading a parallel workshop going on there, and he'll talk a little bit about that here. Okay, so the way it works is everyone will have 10 minutes to talk, and then about 2 minutes for question answering. So we're a little bit sort of tight on schedule, but we'll kind of see how it goes. Okay, all right, and I'll give you guys 1 minute warning before the 2 minutes up.
Thanks, Kevin. All right, so like Kevin said, I'm Reno. I'm a researcher at the COE, the secondary appointment at Hopkins, and there is a second workshop there. Okay, that's known as Scale, and I'll talk about what that is, what the topic is this summer, and how LLMs and VLMs, which are vision language models, are relevant for Scale. So just a quick overview of what Scale is. It's a 10-week intensive summer workshop. It's hosted at the HLT COE. It's focused on hard topical research problems. We do this every year, and it brings together students from Hopkins, faculty from Hopkins, student and faculty from external universities, and then researchers from industry as well, to kind of all work on the same problem. So I think this year we have close to 50 participants, which is 10 more than I expected, but we're happy to have them. So this year, the topic is on video-based event retrieval. So we're just trying to work on testing and improving existing capabilities of retrieval approaches on multimodal content about events. So it started this past week, and a lot of the ideas that I'll talk about are coming out of this, the first week of kind of pitching ideas, talking with people, and also things that we've thought about ahead of time as well. So the motivation for this task, a lot of current data sets on video retrieval are primarily in English, using professional news broadcasts, and by default that means there's very few news sources. But in practice, especially now, real news content is in multiple languages. It's in all different formats. It's coming from thousands of different sources, usually primary sources of people just taking videos of their with their phone and posting it to social media. So real-time news content is shaped by both these professional sources as well as unprofessional sources. So we would really like to be able to do well at retrieving both types of data. So this is the primary data that we'll be working with. I'm speeding through a lot of this, so I apologize if we won't get to everything, but the primary data set that we're using to evaluate is called Multivent, which is a data set that we've been collecting in 5 different languages, English, Chinese, Korean, Russian, and Arabic. And we have about 50 events per language, with about 10 videos about each event with aligned natural text. So this example here, we have the event is some agreements between Saudi Arabia and Iran to restore their diplomatic relations. We have 10 videos about this, and we also have aligned text documents. So that's kind of our primary evaluation set. For a meaningful retrieval task, 2,400 videos is not sufficient. If you think about text IR, you usually have at least 100,000 documents to make it like somewhat similar to a practical, like looking for a needle in a gigantic haystack of documents. So that's what we want to do here for vision as well. If we look at the queries as well, the initial queries were just the descriptions from the video. We have done some adjustment of these, both with large language models and through manual evaluation, to get roughly 48 kind of high-level keyword queries that apply to multiple events, 127 base event queries that we're providing day 1, and halfway we'll provide the rest of the base event queries. So pretty much we're trying to avoid overfitting to the test set, which IR systems have a tendency to be able to kind of really probe and not cheat, but it's kind of close to cheating. And we've had a lot of feedback from our text IR experts as well to say this is probably a good way to do it. And we're also holding out one event type that we'll release halfway through the workshop. But as I said, this isn't enough data. So luckily there is a lot of recent interest in multimodal vision text tasks. So a recent data set called InternVid has come out in the past few months. That's over 10 million videos. from all the language that we care about, plus a few more. And a lot of these cover the categories that we're talking about. They're not explicitly about events, but if we look at them in practice, there are a decent amount of event-based content in here. So it's definitely a reasonable distractor set. So we did not take those full 10 million videos. A lot of them are longer than 5 minutes, and we estimated that it would be about 100 terabytes of space. So we don't have quite that amount of space on the COE grid. Our servers are pretty good, but we kind of decided to take roughly 100,000 as distractors, and we also wrote roughly 500 queries across a small subset of intern-vid to kind of use so that we're not overfitting to multi-event and not kind of like the retrieval mechanisms that we're trying to build are not saying these are multi-event videos, these are intern-vid videos, and kind of just distinguishing between the domains. And then as training, we also have a separate set of 100,000 videos, an additional set of 538 queries from intern-vid, and this is where we're giving the participants all the metadata that they can use, as well as the titles, and also giving the direct video IDs for direct error analysis. So the sub-teams, I'll go really quick, hopefully. So we have 4 main sub-teams. The one largest team is the vision team. So there's a lot of different projects that are being involved there. I'll just say a couple of them. We're working on improving frame selection from these videos, exploring multimodal information extraction, so pulling out specific aspects of these events that appear in the videos, and then building fusion models so they incorporate all the modalities, so vision, speech, text within the video, and any kind of text metadata we have. The second team is combining OCR and ASR. So this is a lot of the non-text ancillary tasks, but they're still very interesting. And some of the things here are detecting OCR-specific scene changes, leveraging outputs from other modalities as additional context to improve speech, and exploring sound event classification. The text team, we have a lot of text IR expertise, and this is a retrieval task, so we definitely care a lot about how well any kind of thing that we could put into a text model does. And we also want to try to improve translations on this very short and noisy OCR and ASR, because current models do not do very well. I can show you lots of examples, but they're pretty bad. And then finally, the team that I'm leading is the infrastructure team. So it's kind of focused on any kind of cross-cutting concerns about the data and evaluation. We have a nice website interface that kind of allows you to look at the leaderboard and submit to this leaderboard and view how well your models and modalities are doing compared to others. And then I'm always focused on generating more and better queries. And we also want to talk about, in this group, ways to generate synthetic relevance judgments. So that's kind of peeking a little bit at the LLMs. So Kevin already kind of talked a lot about LLMs. I just wanted to highlight a few vision language models because that's kind of the primary ones we're thinking about. We are going to look at LLMs as well for different tasks, but since this is a vision scale, we do care about this. So the primary one is GPT-4 Vision. It's trained on top of GPT-4 for next word prediction on image text data. And then there are a lot of open source alternatives that have been coming out recently. The two that I wanted to highlight, well, 2 of them have been fine-tuned on GPT-4 generated data. That's kind of what I talked about in my little comment earlier, just as kind of a teacher-student pseudo framework. But the ones that are most interesting to me are intern VL, because that was trained on English and Chinese, as opposed to the other ones were just trained on English, and it's trained on a lot of OCR. And actually, in their paper, they showed on many OCR tasks it outperforms GPT-4V, so that's very interesting for our OCR team, of course. And then Panda 70M is a vision captioning model, so it's trained on not GPT-4V output, but it's trained on 70 million vision caption pairs, so it should be pretty good, at least at the very specific task of vision captioning. So there's lots of possible applications for VLMs and LLMs. I'll talk about a couple here for each team, but it's really just everybody at the workshop is very interested in using these in some way. So for the vision team, as I mentioned, we can easily think about using pandas or models like Panda 70M to convert videos to text with captioning VLMs. We could also think about summarizing directly because the captions are honestly very short. And for any kind of text model, the more text that we can get that's relevant to the videos, the better. So we can definitely do summarization as well. We also could think about finding the entities with a vision language model, combining with object detection for information extraction purposes. For OCR and ASR, 1 minute, okay, okay, I'm doing okay, I think. So for the OCR ASR team, the biggest thing that we've thought about that's kind of raising a lot of issues with downstream tasks is the order of the OCR is kind of all over the place. We have no idea what text comes before what. So a thought is, can we just ask an LLM to fix the order? And then we also want to evaluate intern VL because as we said, it's potentially very, very good at OCR. For text retrieval, we're thinking about fine-tuning MT-specific LLMs that have come out of Hopkins recently called ALMA to improve on translation of very short informal text. And we also want to leverage any kind of generated text from other teams as well. And then the infrastructure team, as I kind of mentioned, we want to ask VLMs to write queries given these video keyframes. And we also want to try to leverage VLMs for synthetic relevance judgments. It has shown to be pretty good on the text IR side, although recently, I've heard that NIST has had trouble replicating that, but it's still interesting to see. So just very 2 quick examples. This is kind of just looking at entity extraction and grounding. So these are a couple of the images. We can do some object detection, and then we can caption the image either with a longer text from Lava or very short, just saying, pull out the entities and write a quick phrase about them. They are a little bit out of order. Donald Trump is down here, of course, but and then we can try to ground these phrases after doing object detection and captioning using this other thing. So Kate Sanders has been working on this, and it's pretty interesting. And then finally, this is just kind of our initial approach for query generation. So this is without the description using Lava. It honestly looks pretty good. It's a little bit general, but it's not too bad. And if we add in the description, we can see it's starting to actually put a little bit more specifics here. Like we know it's about NASA, so we can talk about NASA here. So this is very qualitative. I'm happy to start looking at these more. I've been staring at queries for months at this point, so I think I have a pretty good sense of what we're looking for here. But at a high level, these look pretty good. So I'm happy to start looking at these. So takeaways, this is the task of event retrieval and understanding is currently pretty underexplored for non-text and non-English domains. So to begin to address this, Scale 24 is exploring video retrieval on event-based content. And every team, and honestly, probably most individuals at Scale even, will be leveraging or testing LLMs or VLMs in some way. The final readout, just kind of as a nice little ad, is on August 6th at the COE. It's open, so feel free to attend. And this is my contact. So, thanks.
Okay, thanks. So next up, we have Shin. So Shin is a PhD student here at Hopkins. She's also in the sign language team, and she'll talk about machine translation. Yeah.
Hello. Is there a difference? No difference? Hello? No.
Go ahead. Oh, it's working? Okay.
It's working.
All right, so take it away.
Thank you, Kevin. So in this very short talk, I'll talk about a very specific application of large language model, which is machine translation. And this is actually our last year's work, and it appeared at the WMT. It's a conference on machine translation. Okay, so for machine translation, it's a basically the task of translating one source language to a target language. And before large language model appeared, people use a transformer for most of the time for machine translation task, and they achieved SOTA results on transformer-based model. Actually, most large language models are based on transformers, so same. Okay. There are many evaluation metrics for machine translation. And so there are mainly 2 branches, which was first utilizing on the left, like untrained models. So you don't need to pre-train a model to, embed the source or target sentence, the reference or your target sentence. And on the right branch, you are utilizing the pre-trained model. So in this talk, we'll evaluate our model based on two metrics. One is blue on the leftmost. So it's based on n-gram matching between the reference sentence and also our target sentence. So basically, it says whether continuous, the consecutive words in your output from the machine translation system appear in your reference sentence. Okay, and a common score basically utilizing pre-trained models to get embeddings of like your three sentences. First, the source sentence and your target sentence, and also your reference sentence. And this is computed based on the similarity between those three embeddings. So basically, blue kind of takes care of the matrix of syntactic features, while comic takes care of the semantic features for the evaluation. Okay, so since LLMs appeared, they have overtaken much of NLP tasks, and for machine translation, like for last year, it's kind of under evaluated. So this table just shows GPT model's ability on machine translation. And in general, there were LLMs with zero-shot learning. They lag behind MT models trained from scratch or dedicated MT models. So I don't think we have time to go through table. I'll just skip this. And also there's some work evaluating other large language models besides GPT models on few-shot learning. It is actually more promising to use few-shot learning for machine translation. And so in this talk, we'll talk about three approaches to adapt LLMs to MT tasks. So first is prompting or zero-shot learning. Basically, we just prompt the machine translation model. Here we use a prompt like translate French to English, and we give it French sentence and English. We expect output of the English translation. And also we experiment with few-shot learning or in context learning. Basically, we first give a few examples of translation. Here we have translate French to English and French sentence, and then the correct English translation. And then we just give another the French sentence we want it to translate, and we expect the translation. Okay, and finally, so this is missing in previous work, which is fine-tuning. Basically, the prompting or few-shot learning, they ignore the abundant data or parallel data we could utilize for machine translation, while fine-tuning utilizes those extra data. Basically, we have these pre-trained large language models, and we continue to train it a large amount of parallel data of machine translation, and then we get a fine-tuned LLM, then we can evaluate from there. But the problem is expensive to fine-tune the entire model. That means you need to load all the model's parameters into your GPUs, and you need to update all the parameters, and LLM is pretty large. I think Kevin already mentioned this in previous lecture, so maybe we can skip this. So we're using QLoRa. I think Kevin mentioned LoRa, so basically Q is short for quantization. So usually large language models are in 16-bit precision, and by quantization, we can quantize it to 4-bit precision. And QLoRa is a basic combination of quantization and LoRa. So this is the data sets we use for fine-tuning. we are focusing on French to English translation, and these are just a number of samples we used. Okay, so we're comparing a baseline model, which is a dedicated machine translation model. It's trained from scratch, and we are evaluating different large language models, like ranging from less than like about 1.3 billion parameters to as large as, for example, Llama 2, 13 billion parameters. Okay, so we've talked about these prompts, and we also evaluated document level translation. So we have designed different prompts for document level prompts. Okay, so I think this is our main results. I think this is the most interesting part of this work. So basically, we're evaluating blue on the top and comet on the bottom. And the orange bars are the baseline model, which is the trained from scratch model. And we have blue bars for zero-shot learning on larger models, and pink bars for fine-tuned models. Okay. So basically, if you just first look at the comet, the scores are actually R or above 0.7. It's a pretty high score. So that means even though you got, various blues, especially for zero-shot learning, you got pretty low blues for certain models. They all achieve pretty high comet score. That means they generate semantically coherent translations, even though they didn't do, exact word matches to the reference sentence. And then just for example, this just shows how fine-tuning can improve over the zero-shot learning, and it is quite necessary for certain large language models to achieve reasonable results on machine translation. And if you compare all the models to the baseline models, actually, most of them, especially with zero-shot learning, they underperform the baseline model. But there's an exception, that is Llama 2. I think by the time we had this paper, there's no Llama 3. I think maybe Llama 3 can do even better than this. Okay. So we tried models, those large language models pre-trained on English-centric data or multilingual data. And so on the left, it's English-centric, on the right is multilingual-centric, multilingual data. So we didn't observe a difference between those models. 1 minute. Okay, I'll just skip this. So I think these results are also interesting. So this is some document level translation. And overall, those models perform bad using just zero-shot learning for this long inputs. But still, Llama 2, they maintain a good performance on long inputs. I'll skip this. Maybe let me see. Okay, this table is just showing how QLoRa can save both the time and GPUs to achieve an equal performance with a model without QLoRa. Okay, I think I'm out of time. And do we have time for QA? Yeah. Yes, please. I think maybe you are mentioning like a domain adaptation, right? So you're adapting the model to the target kind of domain, and some of the patterns of the target data and also the data distribution. Without fine tuning, the LLMs can still generate understandable output, but it might not match the data distribution we desire for the target data set. That's why I think fine tuning improves a lot in terms of blue score, but not common score.
Next up, we have Will Fleshman. Will is a PhD student working with Ben Van Dermeet. That's great, right? Yep. So he'll talk about this idea of continuous training.
All right, thanks for having me. My name is Will. This research was done with a couple other students, Aleem and Mark, and my advisor, Ben. So just a recap of the LLM development process. So this first step is the pre-training. You have a massive unlabeled data set. So Llama 3 from Meta, for example, 15 trillion tokens. So an incredible amount of data. And you're just training for this next token prediction. So there's no like emergent, or there's no specific capability you're looking for except the ability to reproduce this text. And the output of this phase is a pre-trained model. It's generally released to the public in the case of open source development organizations like Llama 3. If you pull that down from a repository, that would be the pre-trained version. Okay, the next step, I only called alignment because Kevin put that in his slides and I wanted to be consistent, so it's funny that he doesn't like that term. That's not normally what I would call it either, but it does make it convenient because the third step is going to be fine tuning. So having a different name is great. But in this step, that same organization usually that released the pre-trained model, they're going to continue training from that snapshot. So they start with the pre-trained weights, and then they're going to train longer, but now instead of the unlabeled data, they're using input-output pairs, maybe questions as input, and they want to do the answer as the output, or some task as the input, and then completing the task as the output, as well as RLHF that he talked about to maybe have the model trained to respond in a human preferential manner. So the output of this phase is going to be yet another model that is released. So for Llama 3, we had the pre-trained Llama 3, and then there's Llama 3-instruct. That's the output of this second step. For Llama 2 is Llama 2-chat. Okay, and then the third task is usually when people like us that don't have millions of dollars to train these things on our custom data, we instead grab those models off the shelf, and then we further fine-tune them for our specific task or our specific domain. But there are some problems with deploying models using this traditional approach when it comes to actual organizations and an industry. So the first challenge is that massive unlabeled data set basically contains all of the internet. And what you might find is some copyright data or some data that you shouldn't have access to made it into that data set. So there's some lawsuits ongoing, right now. OpenAI sued by New York Times because some of their licensed content made it into the training data. So if this is you that's being sued and a judge says, hey, you have to delete the data, you have to delete any artifacts that the data was trained on, this is terrible because you're throwing away millions of dollars of work and would just have to delete the model. So that's one challenge. Also, there's this challenge of catastrophic forgetting. So in machine learning, if you've trained a model and then you train it again on new data, it's sort of like molding Play-Doh. When you get the new training results, some of your ability to perform well on the original data is going to be lost, and the field calls this catastrophic forgetting. So we've done 2 rounds of training, so we're definitely going to be degrading some of our pre-training knowledge. And then the third is this process has no notion of access control. Most data in real organizations are segmented by business use case. There's proprietary data, non-proprietary data, doctor's notes versus the appointments that a secretary might have access to, classification levels in government, that sort of thing. So you would like the model to be able to conform to any access controls that the data you trained on it were privy to. So that's our problem statement. So we want to be able to continuously receive new data, but not forget old stuff. We want to conform to access controls, and we want to be able to efficiently remove data if asked at some point, which beyond the lawsuit case is also just a normal business case like GDPR in the EU. If a user doesn't want a tech company to have their data anymore, they have to delete everything. So this is what we came up with. So the main idea is to use those LoRa adapters that Kevin talked about. So we start with this base pre-trained model. Let's just call it Llama 3. And then all of our data that we want to fine tune with, we segment it into access control categories. So those 3 colors in this slide kind of represent 3 different categories. And then we'll just fit an adapter for each one. And again, these adapters are relatively small. In our case, it was less than 1/10 of 1% of that base model parameter count. So now you have all of these adapters. You need to train or fit a retrieval model that's going to select which adapters are relevant to a query at inference time. So we just take a sentence BERT model off the shelf. So this is pre-trained. And all this model does is embed documents into a single vector representation such that semantically similar documents embed to similar vectors. But those are high dimensional, so then we also do linear discriminant analysis to project those high dimensional vectors to a low dimensional space so that we can fit a Gaussian mixture model on top of them. We use LDA so we can take advantage of the knowledge that we have of which adapter each document belonged to. That way, when they're projected down, you get this space that every adapter is maximally linearly separable. And then the GMM is there to give you probabilities. So at inference time, when a new query comes in, you'll see which adapters are most likely to be relevant to it. You're going to mask out any that user doesn't have access to, and then those are what are applied to the base model. And then later, if document 6 in this example has to get removed, all you have to do is retrain that single adapter, which might take an hour or 2. You don't have to throw away the billions of other parameters that you have in this setup. So here's an example use case. So you have a cardiologist and a person from a finance office at a hospital. Both of them have different access control categories represented by the little colored shapes in the box. And both of them are asking the model the same question. How much does the average cardiac visit cost? Now, we have several different adapters here: billing information, appointment notes, patient records, etc. The cardiologist has access to a different set than the person in the finance office, which you would expect. So those get masked according to access control category. You get the distribution from the GMM. And so the cardiologist response is being mostly informed by patient records, appointment notes, billing information, whereas the finance person is mostly informed by payroll. Those relevant adapters get combined and applied to the base model. And then what you're effectively getting is a customized response to the user's question based on what they have access to. And then in the paper, we show results for sort of those 3, the 3 characteristics that we were after. So these are all perplexity, so lower numbers are better. So if we, and these are 4, modern large language models. If we try to recreate a document when we don't have access to the adapter that use that document in training, you see really bad perplexities. With access, they're good. For the middle graph, that's the catastrophic forgetting experiment. So when you have these adapters laying around, you can always retrieve adapters from years ago and get the same performance. But if you do these other additional 2 fine-tuning strategies that are common, you're going to forget over time as you retrain. And then if you purge a document from adapter, again, your performance is going to fall off the cliff. And then just a brief insight into some follow-on work that this kind of primed. Training on all those unlabeled domains can break down instruction tuning. So it's sort of an open question. Well, how would we get this to work really well if we want to do like question answering on all of this unlabeled data? And so the next project that I did was this readapt thing where you isolate instruction tuning by taking the difference between instruction tuned models weights and the pre-trained models weights. So it's safe off to the side. And then you can fine tune on the pre-trained model, add all that new unlabeled knowledge, and then add in the instruction tuning after the fact. And that works really well for fine tuning with unlabeled data, but still maintaining all that other capability. So with that, I will open it up to questions.
So you have different answers for the same query given your accent.
Right.
For example, can you maybe explain like
Yeah. Right, yeah. So a cardiologist, the doctor and the patient, there's going to be like doctor-patient confidentiality. So when the doctor takes notes about what happened in the appointment, or if it was a psychiatrist, the same thing. The person that's in the finance office or some admin building, they can't access that information. It's private to only the doctor. And so if the doctor has been taking these notes diligently over years and wanted them included in the model, only that doctor can have access to outputs of the model that were informed by their notes. And so they're getting different responses because the model has access to different information.
Well, I would say, like, if I would ask for a question that has one true answer,
yeah,
that, like, wouldn't necessarily one answer be wrong and the other.
Not necessarily. So in this example, they asked how much does a cardiac visit cost? The cardiologist, and the answer for the cardiologist is the patient pays a certain amount, but the finance office doesn't care what the patient pays. They want to know how much does it cost for the hospital, and so they're getting a different answer that's correct in their context. But this is a contrived example. If they both ask a question and they both have access to the relevant data, the answer could be the same. And then also often, if I'm a person that's just interested in, one of these categories and another person is interested in a different category, we're normally not going to be asking the same questions anyway. So this is just kind of a cute example to demonstrate that you might have the same query being asked from two different contexts based on what data those two different user roles have, and you would get a different response. Yep. That's a good question, though. Yep. Yeah, so in the paper, we do both. So what's shown here is this is the diff. So it's going to be a 7 billion parameter difference. We did show in the paper that if you look at the spectrum of that difference, it can be represented really well at low rank. And so instead of picking a specific rank, what we did is picked an explained variance ratio. So for each layer in the network, we will decompose it using SVD to a rank that captures 50% of the explained variance. And so you can reduce the number of parameters up to like 5x for Llama 3, for example, and get sometimes even improved results because you might be kind of taking away any overfitting. But if you're just going to apply the readapter after the fact, it's not necessarily important that you went down to a low rank. But if you then use readapt for adapter swap, where you're keeping all of these around, then you would want the lower rank. Yeah. Yeah. Great question. Thanks.
So next up, we have Andrew. Probably not.
Yeah, he already has it. 10:30. Hi, I'm Andrew, and I'll be presenting our work on benchmarking LLM performance on analogical reasoning. So I'll start off by introducing the definition of an analogy we employed, I guess, in our project. And so we're using the structure mapping theory developed by Gentner in Yes. Okay. Yeah. So yeah, we're using the structure mapping theory, and essentially that's just saying that analogy is an assertion that a relational structure that normally applies in one domain can be applied in another domain. And so what does that actually mean? So as an example, let's consider the analogy, basically the atom is like the solar system. And so in the original paper, they sort of lay out all of the relational structures in both. And so, an atom has a nucleus that attracts electrons, and a solar system as well has the sun, which attracts planets. The nucleus is larger than the electrons, the sun is larger than the planets, so on and so forth. And so because of all these relational structures that are similar, you can say that this is by definition an analogy. And so one question that you might be having is, why should we study analogical reasoning? What makes it useful? So in humans, analogical reasoning can help generate new ideas. And so the example I'll give here is, for instance, the structure of biological neurons really inspired the design of artificial neurons and neural networks. And so you can see that, a lot of new ideas can really come from analogies. And the second thing is that, analogical reasoning can help convey ideas that might be difficult to describe. So for instance, when Isaac Newton was asked, how he was able to make his scientific discoveries, he described it as, standing on the shoulder of giants. And this is evidently a pretty good analogy because it's ended up on Google Scholar. So the research question that we wanted to explore in our paper was, are LLMs, if analogical reasoning is so useful in humans, are LLMs capable of doing the same thing? And so the two research questions, sub-questions really, that we ended up posing are, are novel/creative analogies more challenging for LLMs to identify? And can LLMs find analogies between long-lasting experiences? And what we really mean by a long-lasting experience is, if you consider the example, obtaining a PhD is like running a marathon. Both of these, the source and target domains, entail somewhat long experiences. So a marathon is already a pretty long experience. Obtaining a PhD is a much longer experience. And so because of the relational structures that are similar between either domain, we can say that this is, a fair analogy. So to answer our research questions, we needed analogies between pairs of creative and narratively rich stories. And so the way we went about collecting this data was we asked human annotators to collect 340 pairs of analogous single sentence stories, seed stories. And so as an example of some of this, we have this table where in each row, sentence A is analogous to sentence B. And so we did this 340 times. And to ensure that our analogies were creative, we gave human annotators a story, and then we asked that the second story that they came up with had to include 3 random words. We also instructed annotators to avoid semantic or token overlap because these might count as potential shortcuts that LLMs might be looking at instead of the actual relational structures. And so the second thing we also looked at was, or we tried to do to really get at the narrative richness, was we expanded each of these seed stories to different lengths. So we expanded that, we prompted GPT-4 to extend them to 10 sentence and then 30 sentence lengths to have a variation in, I guess, the length of these stories. So I'll talk about the tasks that we did. So the primary task that we'll be looking at in this presentation is this multiple choice setting where, given a target story, we want to find, the correct analogous story from a set of possible candidates. And so in this example, you have the target story, which is, or seed story, which is, you can't pour from an empty cup. And among these 4 candidates, the right solution is a fallen tree cannot provide shade. We also repeat this for each of the longer settings. So again, we had a 10 sentence setting and a 30 sentence setting. And so we did the same, we had the same setup for each of those settings. So to answer, our central question, can LLMs perform analogical reasoning? We have a table where we just tried a bunch of different models. So we tried, I think, both open source and private models, like proprietary models like OpenAI's GPT-4. We also looked at each of our length settings, the original seed stories, the 10 sentence setting, the 30 sentence setting, and then we reported the accuracies of each of these models on this multiple choice test that we have. And so the conclusion that we came to is that, there's a wide variation of performance in LLM ability. So GPT-4 is able to get, roughly 89% accuracy, which is good, but other open source state-of-the-art models, or state-of-the-art at the time models, such as Llama 2 chat, got significantly worse results. And none of these models are really able to match human performance in just the seed setting. And so here we have relatively decent performance, at least on some models. But once we extend, once we look at the 30 sentence setting, we notice that the performance drops significantly for all of the language models. And I guess human performance also drops somewhat, but not as much as a lot of these language models. And in a lot of these language models, the performance almost goes to trivial. So in the multiple choice setting, because there's 4 solutions, the trivial accuracy would be like 1 in 4, so 25%. So a lot of these models are performing basically at random guess. And so just to display that information in a different way, so to answer the question of how does story length affect performance, on the right here, we have a graph of basically the performance of these different models at the different lengths. And we can see that human performance actually levels off between the 10 and 30 sentence setting, so it doesn't keep decreasing, but all the models that we tested did experience a decrease in performance. We also wanted to pose the question of whether model scale improves performance. So as you probably know, if you increase the model size, it's more complex and it's better able to perform these reasoning tasks. So we can see that scale does. So we looked at each of these model families here. So Llama, X1, Tulu, they all have models of varying parameters ranging from a few billion to like hundreds of billion in size. And so looking at this, we can see that in the single sentence setting, the model performance does improve with scale. But once we increase to the 30 sentence setting, so once we basically extend the stories for a lot of sentences, we see that scale really doesn't afford that much of an improvement in performance. So so basically just as takeaways, to answer our first research question, are creative analogies challenging for LLMs? So the analogies that we created did pose a challenge to some of the LLMs that we tested, but there was quite a variation in the performance that we saw. And then to answer our second research question, can LLMs find analogies between long-lasting experiences? We found that performance generally degrades as you really increase the length of the narrative. And also that model scale does not really help with this, the performance on these longer settings. Yeah, thank you.
Thank you. I assume for like applications, you wouldn't be having it take a multiple choice test. So like where, I guess, where could the research be useful?
Right, so we are considering the setting where what we actually originally set out to do in this paper was have this almost like analogical retrieval setting. So instead of having like a multiple choice between, you're given the story, you're tasked with finding the correct story from, 4 candidates. We wanted to try like hundreds of candidates. And that's, I think, more akin to almost like case-based reasoning where, you're trying to come up, you're trying to see like based on prior experiences, what might help you with like a current situation or something. And so we tried that task and it like failed miserably. Like the performance is basically trivial even for like GPT-4. So that's why we like to have meaningful results. We scaled it back down to this multiple choice setting. But these results are also in our paper if you're interested in seeing it. Other questions? Oh, yes. So that's a great question. This is a question we also had as well. So the way we ended up testing for this was we basically took the the longer stories, and then we asked if we asked like the state of the art, like GPT-4, if the shorter story still entailed from the longer story. And so I think large language models are sort of understood to solve the textual entailment task. And so when we fed these short, like when we did the set up the task, so it was like a textual entailment problem between this seed story and the longer extended stories, we got like accuracy, I think in like the upper 90s. I don't remember the number off the top of my head, but this is also in the paper as well.
All right, so next up is Raphael. So Raphael is also a PhD student here working with Nick Andrews. He's going to talk about machine-generated text.
Great. Can you all hear me? Great. So I'm Raphael, and I'm going to be talking about our work on detecting machine-generated text using stylistic representations. So to start by motivating the problem, imagine that you're a conference area share and you task a group to review a paper. Now, the problem in 2024 is that some of these reviews may be machine generated. And so really the question is, how can you detect these? And unfortunately, that's not a contrived scenario. I know people who have actually been victims of this exact same thing. So there are usually 2 paradigms in literature on doing this. The first one is to use the conditional token-wise probabilities of a language model. And so this is where you essentially send your piece of text through something like a llama 3.8b, and then you essentially capture some statistic like perplexity or log rank or something else that makes human text separable from machine text, and then use that to threshold. And the second paradigm is to essentially train a classifier in the usual supervised manner in order to detect machine-generated text. Now, the problem with both of these approaches is that they are prone to underperform as soon as you sort of shift your testing domain. So here on the right-hand side, you have a ROC curve for a classifier we trained. And the blue is when the train and testing conditions match. And all the other curves are when you change any variable of your testing conditions. Now, either you're sort of testing on a new LLM or on a new domain or on a new topic, and you'll see that a lot of these detectors sort of underperform. And this is sort of a well-known finding at this point. So instead, for this work, we sort of always assume that there's some domain shift that's going to happen. And so we essentially work in the few shot scenario where the area share will essentially prompt a set of popular large language models to generate some support set that they are going to use to build a few shot detector that is then going to make predictions on whether things are human generated or machine generated. And really sort of the main insight of this work is that stylistic representations trained on human authors, so these are representations that captures the style of human authors, are able to separate language models from humans. So on the left-hand side, you have sort of your typical sentence BERT embedding where points are close together if their semantics are similar. And in the right-hand side, you have a stylistic representation where points are close together if sort of their style is similar. And what you can see is that sort of human text sort of clusters on its own, and all the different language models are sort of far apart from these humans. But also, more interestingly, at least to me, you know, things like ChatGPT and GPT-4 are separable. And so this is sort of an interesting finding. I think that a lot of this happens because sort of language models, I think, learn an average of the style of all the training data, and human style is really a lot more fine-grained. And so that's probably why you're seeing the separation. I'll make one extra comment on this. If you're sort of interested in getting language models to sort of talk more, well, write more like humans, I would look at sort of Aline Khan's work on this. So he was sort of in the first slide of this. He's a collaborator in this work. He works a lot on sort of trying to get large language models to follow interesting constraints like generate in a specific style. Okay, so now I'm going to go into sort of how we train a style representation model. So this is not an LLM. This is sort of like a classic representation learning model at this point. But essentially, our style representation really takes W pieces of text from 1 through 16 usually. And usually in training, we sort of we sample this according to some distribution. And then what we're going to do is we're going to take W documents from the same author. We're going to take some random but consecutive document tokens from each sample. And we're essentially going to send this through SBERT initially and learn an aggregation function over all of the W embeddings. And we train this, I guess, in the usual supervised contrastive learning way nowadays, where points, you want your positive points, so your writings from the same author to be close together in the embedding space and far away from everything else. And there are sort of some hyperparameter you know, listed in the slide. And the reason I list these hyperparameters is because all of these hyperparameters are very important, and these models can tend to be quite sensitive. So now we're going to go into sort of more of the experiments. Given our motivation, we sort of evaluate only on unseen domains, topics, and language models, right? So if we trained our style representation on Reddit, we're going to evaluate on everything else that's not Reddit, including sort of Wikipedia, WikiHow, PeerRead, Archive, and Amazon. And usually for all of the experiments we're going to see, the experimental setup is something like this. You're going to randomly select one episode, where an episode is essentially a set of writings of size n to serve as a support sample. And so the support sample is sort of few shot lingo for this is what you get to see. You know, I give you 5 writings. Then you're going to group all your queries into sort of episodes of the same size. The queries are essentially your test samples here. And you're essentially going to use cosine distance as sort of a measure of how human or how machine generated it is. So in our paper, we essentially studied 3 different scenarios. The first is sort of single target. So this is answering the question, was it written by ChatGPT? Multiple target, which is, I think, more interesting, is sort of, was it written by one of the set of the popular LLMs? And then we also evaluate the robustness against paraphrasing attacks. Usually, you can show that you can evade detection by taking the output of a language model and then paraphrasing it with some paraphrase model like Dipper. Okay, so this is a big table with a lot of weird symbols. So the first thing is like, okay, what is the metric that we're optimizing for? This is PAUC. This is the AUC restricted to the operating points where the false positive rate is sort of less than or equal than 1%. So that's your your very left-hand side of your ROC curve, which is usually what you care about for operational settings. We have a bunch of different training data sets. We created this AAC training data set from sheep LLMs such as GPT-2 and OPT. And so we studied whether sort of adding LLMs into the training of some of these methods improved performance or not. And N is essentially just the number of few shot samples that you're given, right? 5 or 10, for example. And I think that the main takeaway is that, actually I should have highlighted the first 4 rows, but the first 4 rows are all stylistic representations, essentially. And what we see is that stylistic representations trained only on humans, right? So we've never seen language models during training in our life, are very good at separating humans from machine text already. Okay. And that is interesting. Did I do that?
I think this happens.
Oh, okay. I have none. Oh. Is it Zoom okay though?
I think Zoom's okay.
Okay.
So it's just the projectors.
Yeah. Yeah, that's okay. Okay, and I think we're back. So yeah, so the next thing I'm going to talk about is sort of this paraphrase attack scenario, right? So what if the reviewers had used a paraphrasing model to evade detection, right? So they use an LLM first, and then they use something like Dipper. So you can essentially also play the same game with all of these detection methods, right? You can yourself preemptively paraphrase your support set and include that into your detector. And then measure performance with and without doing this. Sort of that's what we do right here. The main takeaway is sort of the yellow curve is including the paraphrase examples in your support set, and the other 2 curves are not doing that. And so as the proportion of your support set gets paraphrased, of your queries get paraphrased, your performance usually goes down unless you include that in your support set. And yeah, I think that's it. So to conclude, really the main thing is sort of the few shot aspect of it, and also the fact that stylistic representations are actually quite good at detecting machine versus human. Any questions?
Generated text, like sometimes falsely flagging things written by non-fluent speakers of languages, of like the languages that they're writing in as machine generated. Is that like something that you've been testing for specifically, or?
We haven't been testing for that specifically, but no, that's a very good point. Yeah, something we should test for.
Right, so last but not least, we have Michael. So Michael works with Andreas, and he's actually from the hardware world, so I think this will be interesting.
All right, yeah, so looks like the formatting got a little messed up there. Hopefully everything is good for the rest of the presentation. So yeah, as Kevin mentioned, I'm from the hardware world, so this will be a little bit different spin on things than compared to the previous talks. Yeah, so I'm a 5th-year PhD student in Andreas Andre's group here at Hopkins. Yeah, and we do chip design for a variety of things. So this project is kind of a recent spin-off of a summer workshop that we go to, where basically we were summer 2023. ChatGPT was kind of all the rage. So can ChatGPT generate kind of Verilog, which is sort of the schematic entry point for hardware design? So it's very similar to kind of programming languages with a little bit of a twist that I'll talk a little bit more about in the next couple of slides. So for those of you who might not be familiar with, ASIC stands for Application Specific Integrated Circuit, and it's a kind of growing field, kind of especially kind of forced by AI and these kind of innovations that you guys are all talking about here. People are spending more and more money on buying more and more complex chips. And so, yeah, this is kind of a growing, interesting field. And we're seeing kind of if these large language models can help us design bigger and better chips faster is kind of the question here. So roughly, this is kind of on the left, like a pipeline, or if you will, of the hardware design phase. So you start out with a concept of our idea, maybe like a rough block diagram, kind of what your inputs, what your outputs are, what kind of the architecture looks like at a rough level. Then you go into kind of this key step here is the functional and logic design. So if you're familiar with kind of basic electronics, you might have drawn resistors and capacitors on a schematic type of a thing. These days for digital circuits, we don't really do that anymore. We have hardware description languages, which we'll talk about Verilog here, where basically it's a programming language that we can basically map directly to digital circuits. So you give me a piece of Verilog code and I can draw on a whiteboard for you what that schematic would look like. This is a number of benefits, mainly that we can write much more complex code a lot faster than actually drawing the schematic by hand. So there's a lot of kind of benefits from abstraction, similar that you get from writing in Python, say, versus C. So yeah, that's kind of the key thing we're looking at here is this kind of writing the Verilog description code. If ChatGPT can generate Python code or other software languages, how well can it do for Verilog? So yeah, kind of the proposed solution here is kind of what we're seeing. Basically, can we just, in kind of natural language, pretending like I know nothing about hardware design, like, hello, could you please provide me a Verilog description of an 8-bit counter? And so this is roughly the code it spits out on the left. So a key kind of like structural components of Verilog code, basically we have our inputs and outputs here in the module kind of declaration, and you have kind of the core logic components inside. So it's a little bit different than traditional programming in a couple of ways, mainly that basically you have a bunch of these always blocks that are all kind of in parallel. This is very much similar to a parallel programming language where each one of these blocks kind of operates sequentially, but then each block operates in parallel. And then since we're dealing with hardware here, there's a lot of kind of fixed point arithmetic. We're dealing with individual bits and things like that. So kind of being sort of neuromorphic engineers, we also decided to kind of challenge ChatGPT, if you will, by trying to design basically spiking neural network accelerators. So similar to the neural networks that you guys are using here, but the kind of primitive neuron element is more similar to a biological neuron. The main motivation here for us is basically we expect that ChatGPT has seen less training examples of this kind of code. So we have kind of a weird design. There's probably not that many examples. Actually, in the paper we published on this, we just went on GitHub and searched kind of a bunch of keywords and saw how many results there were. If I recall correctly, there were on the order of maybe 10 examples of Verilog code related to this on GitHub. So it'll be some interesting results to see how well it can synthesize this kind of logic. Yeah, so just kind of, again, mentioning spiking neural network. Main motivation here is that it's a relatively unique system for ChatGPT to deal with. So kind of the uniqueness of the design and the uniqueness of the kind of desired output language. Yeah, so let's see kind of how that all performs. So this is kind of basically the rest of the slides kind of going just through this kind of primitive neuron. So what we're designing here is a leaky, integrate, and fire neuron. Which basically all that means is kind of a continuous time system. Basically, you get 1-bit inputs that are kind of coming in time. And as you get that, you increment kind of a local counter variable. And then once that counter reaches a certain threshold, you then generate an output spike that goes off onto other neurons in the network. So kind of starting off in the top left, can you write me a Verilog module for spiking, leaky, integrate, and fire neuron? Please include a multi-bit current input and a refractory period. So this is kind of if you take any kind of computational neuroscience class, this is kind of the first type of model you'll learn about. But yeah, so then ChatGPT goes right ahead. Sure, I'll give you a basic model. Has a little description that's not super important. And then it spits out some Verilog code that at first glance, it looks very good. Like it would probably take me on the order of half an hour to write all of this, to think about it and kind of generate basically all the lines, generate the structure and kind of get it all set up. So now kind of we have this code that, like I said, at first glance looks good. Let's kind of dive into it and see how well it actually performs. So there are a couple of kind of fundamental errors. I kind of broken into syntax errors and logic errors, where syntax errors would be the kind of thing that you throw this into your compiler, basically, and the compiler says, hey, this code's wrong. I'm not going to deal with this. So that's basically these errors on the left-hand side. So basically, the output variable here has no basically type declared, and it needs to be declared as a register. That's basically a function of how it's used down here. So all the inputs are declared as wires here. The output could have been declared as a wire, but the way that it's used down here basically requires that it be a register type. Similarly, we also have our output register that is being multiply driven. So I mentioned that these always blocks kind of operate in parallel. And so it's kind of basically, the tools don't know how to handle this type of situation when you drive the same variable from two always blocks because they're operating in parallel. So then who has precedence and that kind of thing. And that all needs to be avoided basically when you're writing your hardware description language. So those are kind of the syntax errors that are kind of pretty easy to identify. And then there are also some logic errors mainly related to that counter. So we're not in Python here with 32-bit integers or floats or anything like that. We have basically 8-bit counters here, so we can count 0 to 255. That's all unsigned 8-bit counters. And so you need to handle overflow and underflow situations when we're adding and subtracting from this 8-bit counter. And so basically the way this logic works is it doesn't handle the overflow or the underflow, and so you get a lot of weird behavior. I think I have some simulations of that basically showing that here. So yeah, this is an example waveform on the bottom, basically showing the overflow case. So I'm feeding in an input current of just 100, and we're looking at the counter in this bottom waveform here. And you can basically see the counter goes from 0 to 99. So it's incrementing from 100 minus 1 due to the leak rate. So it increments to 99, then to 198, and then it all the way increments and rolls over to 0, which is kind of like, what happened? Basically, we skipped over 255, and kind of this overflow didn't really happen. We didn't even generate an output spike, and basically nothing happened. Our neuron is kind of dead in the water, if you will. So we're actually able to ask ChatGPT, hey, can you fix this error? Or hey, you have an overflow error. Can you please update the code to account for that? And so it generates the new code, and then the new waveform down below is shown correct. So sorry, I misspoke a little bit earlier. This is actually a correct waveform. In the incorrect waveform, basically you see that it increments from 198 over to whatever 255 minus 100 is. Yeah, so kind of keeping going through this. So the overflow issue is pretty easy to fix. All things considered, identified the issue, asked it, hey, can you please fix this? This type of thing would be very amenable to say, like some kind of automated framework, as I believe one of the earlier talks talked about, where you could integrate this with your Verilog compiler. ChatGPT could then see the error, fix it, and then finally output you directly output you the correct code that you want. With the underflow issue, we actually had much more problems. I think if I remember correctly, it took maybe on the order of 7 to 8 prompts to fix this, where basically we would ask it like, hey, you have this problem, can you please fix it? Basically having to get more and more specific. And then kind of near the end, it actually managed to fix it, but then it reintroduced the overflow error. So it's kind of playing like this ping pong game of trying to get this relatively simple piece of code actually kind of completely clean and simulating correctly. So yeah, eventually we were able to get the neuron completely programmable, but it took a fair bit of work. Basically, we had to kind of just look through the code, simulate it kind of as we were going through this process, and kind of walk ChatGPT through the steps to kind of get it completely functionally correct, if you will. Once we were there, though, we were actually able to make changes to the code pretty quickly. So in this instance, the original kind of base module that we started with, wasn't really programmable from the interface. And so we just asked it, can you make the 3 parameters that you had programmable? And it refactored the code kind of exactly as we would expect. And so this was pretty cool to see. So as far as like code maintenance and things like that, it did very well. So I'll skip through this. Basically, we kind of went through the rest of these prompts to generate a full network. The network was pretty simple, especially on the scale that you guys operate with. I think it was 6 neurons in total, basically 2 layers, each with 3 neurons in a fully connected fashion. This system was fully programmable via SPI and kind of fully connected. So it was sort of kind of incredible that we were able to go purely from natural language to a functional Verilog description. So yeah, basically this was one of the first fully just like AI described ASICs, if you will. We went entirely from natural language to Verilog. So unfortunately, I don't have a picture of the layout here, but the whole basically chip that we taped out was purely described with natural language. There was no human written Verilog in that ASIC. It was submitted to Tiny Tape Out 5, and we're expecting to get the actual physical hardware that was designed by ChatGPT back sometime this summer. We have another iteration of this that we sent out on Tiny Tape Out 6 that should be coming back later in the fall. Yeah, any questions? Yeah. Yeah, that's a great question. Definitely, I think in this case, it would have been faster for me to write it myself. I think this is kind of similar to what people have seen in the software side of things, like in Python. It can get kind of close. So you can ask it to generate you a module, and then use that skeleton and basically kind of fix the errors yourself. There's probably like an optimization point to where how much you rely on it to generate your code versus manually fixing the errors. That is probably more optimal. For actually fixing these errors, there were a lot of iterations that basically I looked at the code, I saw it was incorrect, and I iterated and asked it to fix it, which is relatively quick. But then I think the underflow error, for instance, I didn't notice when actually looking at the code. So I had to go all the way through kind of writing my test cases and actually simulating it to see the error. Like, oh, why is this not working? And so there was kind of a long iteration process there.
Great. All right. So that's the end of this session. Let's thank all the presenters again. Great job. Okay, so now we have a lunch break. And so lunch, and then if you want to set up your computer stuff, please come back at 1 o'clock. From 1 o'clock to 1:30. Dan will be around, right, at Malone for helping people out. And then at 1:30, we will start the lab section. So just to note, we'll be meeting at Malone Hall, so not here. So next door. Before I end, Paula, is there anything you want to announce?
That it seems that the Levering cafeterias are not open, so we have like other options. We have our house, the one that Sanjeev was mentioning is like a 10-minute walk, or go to the other side. We have Bird in Hand and other cafeterias. Just like go straight that way, right? And you will find the cafeteria. They are outside the campus. You have to cross the street, and you will find Barnes & Noble on the left side, and you will find Birds in Hand on the other side. And what is the name of the other Cajun or something like that? Cajun, that is Korean food. And you will find Chipotle. I don't like that, but anyway, everyone has its own opinion about that. Okay, so let's reconvene at Malone 122. So it's gonna be a different room, okay? Look for Malone 122. It's just 2 buildings from here, okay? Malone 122, okay? Okay, cool. Okay, so see you later. Where is my list? So there are some folders over there for the summer school students. You can take one, okay? Look for your name, okay? There are some folders with information there, Okay? Oh, okay, thank you.
So for the speaker. So.
Okay, okay, thank you so much.